Hi, my name is Paris Wolf, and today we're going to be learning cryptography. The Bifid cipher. It's a grid that matches letters into numeric values. It's a 5 by 5 matrix. So you just need to remember that it matches letters into numeric values and it's a 5 by 5 matrix. If you're interested in learning how that works, you have the two rows here, or the horizontal columns, and the 4 matches the M, and then this lines up with the 5, bringing you down to the M. So they just intersect there at that point, and then that's how you're going to get the ciphertext. For the Playfair, it's a 5 by 5 grid created with a secret phrase, and letters cannot repeat in the grid. And to repeat for the Playfair, this is the important part, it's a 5 by 5 grid created with a secret phrase, and letters cannot repeat in the grid. So the difference between the Playfair and the Bifid is that the Bifid matches letters into numeric values, while the Playfair is using a secret phrase. Now, since it's a 25 by 25 matrix, J is not included in that matrix, and it's interchangeable with the I. For homophonic substitution cipher, you need to know that it replaces the plain text with many possible ciphertexts. And to show you what that means is that here we have the letter H, which is matching up with the ciphertext of 19. However, when we're looking at H, it could be any one of these numbers below this H, and all of these would represent the letter H. Now, vowels, because those come up more commonly in the English language, they're going to typically have a lot more ciphertext or possibilities that way to make it more difficult for frequency analysis to be able to break that. So Caesar coding. This was created by Julius Caesar and typically used a 3-letter shift. And so if you have the letter C, it goes to D, E, F. With the letter A, B, C, D. And when you get to the end of the alphabet, such as Z, it's going to wrap around the alphabet to A, B, C. The scrambled alphabet. Now, each letter in the alphabet is mapped to a random letter, such as B connected to T, or C connected to H, and so on until all 26 letters in the alphabet are connected to another letter. This is analyzed against ciphertext to identify text variation to standard English characters, and so they cracked it with frequency analysis. The Vigenère cipher, also known as a polyalphabetic cipher, and uses a number of cipher alphabets. Its popular method is to use an agreed upon code word. In this option here, we have the keyword of green, and it just repeats to the same length of the plain text. And the output here on how you would figure this out is we match G with the keyword, and then H is the plain text is hello, how are you? And we map this all the way out, giving us a ciphertext of N. And as you can see, it's A through Z, and then the next row here starts with B. It was cracked with the Kasicki examination to determine the key length. Morse code. So with Morse code, you need to know that it uses pulses of electronic current along the wires with silence in between them, and it translates characters into dots and dashes. Now, dashes last 3 times longer than a dot and a longer delay between words than letters. Here's what the Morse code looks like. Now, fractionated Morse cipher, that is a variant of the Morse code and adds an extra layer of encryption to the traditional Morse cipher and uses a 26-character key mapping and converts the plain text into Morse code into like fixed length chunks, and then it's converted to ciphertext letters. Pigpen uses a MonoAlphabetic substitution method, and it's a 4 grid in a square in a diagonal shape. If you would like to see me how this actually works, then go ahead and leave a comment below, and I'll do a full video on that. The issue with Pigpen is that once the mapping is known, it's difficult to keep the message a secret. Railcode. Now, railcode scrambles the plaintext in some way where it's not possible for the human eye to spot them, and this scramble method is known as the rail sense cipher, and a message is written in a sequence across a number of rails. So here is the ciphertext here. When you try to read it from left to right, you can't really understand, like what's going on here. However, with the cipher method, you just can read from here. We are discover, we are discovered, flee at once. And so once you kind of know what you're looking for, it's easy to spot that pattern. But initially, it was very difficult to crack. So combinations. Combinations represent a selection of items from a larger set without regard to the order in which they are chosen. So by giving you an example of representing a selection of a larger set, let's say we have 3 countries, and then you go ahead and pick 2 of those countries and put them in different orders and combinations, such as American Iceland, American Germany, Germany and Iceland. There's only so many ways that that combination of 2 can be chosen out of the 3. So the combination represents selections of items from a larger set. Now, permutations. Permutation is an arrangement of objects in a specific order. More formally, a permutation is a set of distinct objects, is a reordering of those objects. So let's say we have 3 countries. Well, there's going to be many different ways that we can arrange those, and that's going to be like 3 to the factor of 2 times 1. So I'm not going to read all these off here, but we have like America, Iceland, Germany, American, Germany, Iceland, and it just has all different permutations or arrangements of those objects. While combination is only selecting a portion of the total amount, or the larger set would be the correct term. Set theory. Now, set theory is a well-defined collection of distinct objects called elements or members, which can be anything from numbers, letters, colors, or even other sets. Sets are typically denoted by curly braces, such as A, curly brace, 1, 2, 3, enclosed. The one-time pad is a cipher code that is used only once, it's near uncrackable, and it uses a code book that both parties know. Data. So computers read data in binaries 1 and 0s. ASCII uses 8-bit values and supports 256 different characters, and UTF extends those characters to a 16-bit value, giving 65,536 values. Here's an example of what they look like. Now, typically ASCII is used to represent the English language. Hexadecimal. Hexadecimal involves splitting the bit stream into groups of 4 bits from values 0 to 15. And so let me go ahead and break this down here. So here is the hexadecimal, and this first line here is either on and off, and this is going to be the 1. So it's either 1 or 0. The second line, if it's on, it represents either 2 or 0. The third line here is either going to be 4 or 0. And then the last line here is either going to be 8 or 0. And so you add those up. So since this is on, it's 8. The next line is 0. The next one is 2. You're going to add all 4 of these up. It equals 10. So that 10 lines up. It looks just like this 1, 0, 1, 0. And that's the letter A. In the next example here, since just the this bit here is on, that equals 8. And so that's going to actually equal the hexadecimal value of 8. And for the last one here, all the bits are on, and that's 1, 1, 1, 1, or 8 plus 4 plus 2 plus 1 equals 15, which equals the value hexadecimal of F. Now, your computer reads data in binary, and so that's either 1 or 0. For on is 1, and off is 0. So if your computer can read an internet speed of 50 megabytes, that's a big number here. That's 50 million bits per second with an internet speed of 50 megabytes. So for data integrity, that's the proof that something has not changed, and the cyclical redundancy check is added to the end of the packet, and it's checked for any of those binary digits to make sure there's no errors. Now, if there are errors, well, one of the systematic methods or algorithms that they use is the Reed-Solomon that checks the integrity and also will correct them. It's also done at a higher level, such as within the OSI model or the TCP model, for fixing those errors. So with the Huffman coding, it's a compression technique that looks for patterns in the binary data. And so here we have the letter and the number of occurrences, and it keeps track of that and places a different symbol in there to shorten the length of the message. Now, the Lempel viz Welsh is an adaptive dictionary data compression technique known as LZ-77, and it's a basis for many of the most popular compression methods, suited for a high degree of repetition. And here's an example here. We have the word receiver, and since RECEI shows up many times, it's using this compression technique throughout here to go ahead and shorten the message. LZ-78 extends the LZ-77 by building a dictionary of frequently used groups of characters. So little endian, that is the order of bytes stored depending on the computer's architecture type. And when the least significant byte is stored in the lowest memory address, that is known as little endian. And when the most significant byte is stored in the lowest memory address, that is known as big endian. And it really just depends on the computer architecture type. It doesn't really matter like the size of the environment, whether it's a large enterprise or a home environment. It only has to do with the computer architecture of the system. So with Intel processors, those typically use little endian, and with the IBM architecture mainframes, that uses big endian. So today we're going to look at integers, rational numbers, real numbers, complex numbers. Integers can be positive or negative and have no fractional part, and they're represented by like 3, -4, 8, -7. Rational numbers are fractions, such as 3/4, 1/2, and real numbers are both the integers and the rational numbers, such as 2.3. Prime numbers represent integers and can only be divisible by 1 and itself, and natural numbers represent positive numbers such as 1, 5, 16, or any number that's a positive. And I just want to point out that a number such as 3 is both a natural number and a prime number, so some of these can have multiple attributes associated with them. Today we're going to be learning binary math for how to accept or, and. So the first thing you need to know about accept or is that if one but not both of the numbers are your acceptoring, then your answer is going to be 1. So with 1, it lines up with the 0, and that's going to carry down to a 1. On this next line, with except or, since they're both 1 here, that's going to be a 0. So I'll show you the solution here. With 0 and 0, it's carrying down to 0. Another 1 and a 1, that's a 0 with 0 and a 1. So since one of them are 1, it has to be that one of them are 1, and it carries down. And the next line here, this would be the data line, and then the second line is going to be something like the initialization vector. When you're acceptoring 0 and 0, comes down to a 0, 0 and 1, you have a 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. Okay, we'll look at one more here for acceptor, and then we're going to look at the next ones. So with 1 and a 0, carries down to the 1. The 1 and the 1, the 0, 1 and a 0, the 1, 1 and a 1, it's a 0, 1 and a 1, it's 0. So you need to be very careful when you're reading any sort of question, because if it says except or, then you're going to have to perform this mathematical way. If it says or, then you just need to pay attention, because with the 1 and a 0, it's still going to carry down, but with a 1 and a 1, it still carries down to a 1. So if one or both of the numbers you're ORing is 1, then your answer is 1. Now, if they're both zeros, we'll take a look at that. Then it's going to carry down and be a 0. So with OR, you just need one of the two lines to be a 1, and it'll carry down. So if they're both 1s, then it carries down to a 1. Now, with the and means both have to be. So if both the numbers you are anding is 1, then your answer is going to be 1. So with this, if it's a 1 and a 0, it's a 0. 0 and a 1, it's a 0. 0, 0, it's always a 0. With a 1 and a 1, then it carries down. So you really just need to pay attention if it's an except or, and an and. I want to hit some key definitions here. So cryptography, that is the science of keeping information secret and transforming that data. So that's taking plain text data to ciphertext. Plain text data is an unencrypted message. The ciphertext is the output of that encryption process that is then the encrypted message. Cryptanalysis is the art of breaking or cracking that cryptography algorithm. And then cryptology is the study of both cryptography and the cryptanalysis. The mod operator. The mod operator provides the remainder of an integer divide, and the mod operation often involves a prime. So this is a technique they use to help break encryption by identifying the prime number. So 17 mod 5, that's 17 divided by 5, which is 3, and giving us the remainder of 2. So what we're looking for is the remainder, because it's 5, 10, 15. So 17 minus 15, answer is 2. 13 mod 2. 2, 4, 6, 8, 10, 12. 13 minus 12 is 1, because the remainder is 1. 37 mod 11. 11, 22, 33. So 37 minus that 33 gives us a remainder of 4. So the answer is 4. You have to know how to do the mod. Now, shift operators, this is a technique that they know, or is defined as rotation, and is to help encrypt the data. And with this, the bit shift operators can be left or right. And so here we have the input, and they're shifting 4 to the right, and then this set over here is moving 4 to the left, and it just continues down. Random number generators, there's 2 different types. There's the pseudo random number generator. It's very fast, but it's deterministic. So if someone's trying to identify the random number, it's a lot easier for them. So they use this typically for simulation and modeling, and it's not like a true random number. While a true random number is a real random process. And for example, it monitors the movements of a mouse on the screen or pauses between the keystrokes. The method is a lot slower, but it's a lot harder to determine what that random number is, and they use this in things such as gambling games. So the MonoAlphabetic cipher is a substitution cipher where the letter matches up with the same corresponding letter in the ciphertext. So it's a 1-to-1 ratio, such as in the Ceasar cipher, it's shifted by 3, so A to D, and A always matches D. In the polyalphabetic cipher, that's when you're using multiple alphabets. You can see there's just a huge list from A to Z, and then it starts at B to C, and so on, so on. This is an example of a Vigenère cipher here, by the way. And so it matches multiple alphabets to encode the plaintext. So the difference between the monoalphabetic cipher is 1-to-1 versus 1-to-many. The Enigma machine. That is a polyalphabetic substitution cipher that does not repeat within a certain time frame, and along with the secret key. The weakness that it had is that none of the plaintext letters could be ciphered. Asymmetric encryption, that's when you have 2 keys, a public key and a private key. The public key is used to encrypt the data, and the private key is used to decrypt the data. Symmetric encryption. That's when you use 1 key for both the encryption and the decryption. It's a lot faster than asymmetric encryption. As far as the encrypt and decrypt, they're using the same exact encryption formula with the same exact variables that are going to that encryption variable. And the term that is typically used is a shared secret key. With frequency analysis, you're analyzing the ciphertext to identify text variations and comparing it to the standard English characters. And so with this ciphertext here, we're noticing, okay, here's A, and it shows up 8.5% of the time. And so you're looking for things such as vowels that appear much more often to help figure out the message. So with Diffie-Hellman key exchange, that's an asymmetric key exchange algorithm to set up symmetric encryption. So it securely exchanges the cryptographic keys over the public channel. It is interceptable to the man-in-the-middle attack, but they never actually send the keys over. And so what that means is that this server over here and this computer over here, they're able to come up with a public-private key so they can exchange information without actually passing it over the internet. And so it's more secure than setting symmetric keys, because if that gets compromised, then they'll have everything. So it's asymmetric to be able to set up symmetric encryption. And the reason why is that symmetric encryption is a lot faster. So you need it'll take a much smaller key size and able to have the same level of encryption and security versus an asymmetric key exchange. It's a lot slower. The computers need a lot more processing power, and the key size has to be a lot longer in order for the encryption to be the same level of security as a symmetric encryption key. Now, perfect forward secrecy, that means a new session key is used to encrypt the communication each time. And this is very important to know, actually. And so let's say we're talking on the phone, and with this session, it's encrypted. Now, if we talk tomorrow, the perfect forward secrecy or the Diffie-Hellman key exchange it communicates a new key each time that we talk or communicate for each session. And that's why it's called perfect forward secrecy, because if they compromise one session, they don't have all that past information because it was a new key each time. So if it's just Diffie-Hellman, that means they're using the same key every time. So elliptic curve Diffie-Hellman, this uses perfect forward secrecy, and so with this, each time it would have a new session. And so this is the concept, perfect forward secrecy, and this is the algorithm that actually implements it each time, the elliptic curve Diffie-Hellman. We're going to take a look at the different cipher modes here, starting with electronic codebook, which is the weak and the most unsecure mode. So block 1 here, this represents the plain text data, and this is going to go through an encryption algorithm, such as Advanced Encryption Standard, creating the Cipher 1 text. What you need to know about electronic codebook is that each block of data is going to be processed separately, so they're independent of each other. And if the same input or plain text data is put into the block and then encrypted with the same algorithm, then the cipher is always going to be the same. It is weak against copy and paste attacks, and that's when the attacker could copy and paste the cipher blocks from one part of the message to another. And if the attacker observes identical ciphertext blocks in different parts of the messages, it indicates that the corresponding plaintext blocks are identical. With cipher block chaining, this one's a little bit different. We have the block 1 plaintext data, and that gets XORed through the initialization vector with one of these processes, XOR and or, and then it gets encrypted. Now this one here is a lot different because after it gets encrypted, cipher 1 is now used as the initialization vector for the next block of data. So block 2 is now going to XOR the cipher 1, and then that's going to get encrypted, creating cipher 2, and then cipher 2 is going to go to block 3, and block 3, or the data set 3, is going to get XORed with cipher 3 with the encryption, and then putting out output cipher 4, and so on until the end of the message. Now, this initialization vector, this goes back to the math in bits here. So block 1 represents the data, and the second set sets up the initialization vector, and then the output. This is what's getting encrypted here with the encryption algorithm. So you just really need to know that the cipher block chaining incorporated the initialization vector, and the definition of the process would be uses an initialization vector to encrypt the first block. It's randomly created this first initialization vector, and then uses the results of that encryption cipher to encrypt the next block. I do want to note that the initialization vector has to be sent with the ciphertext in order for it to be decrypted. The first step for cipher feedback is the initialization vector, which is randomly generated or created. That initialization vector then gets encrypted with an algorithm such as Advanced Encryption Standard, and then the output of that is XORed. Now, this XOR has multiple different outputs. One output goes with block 1 and creates that self-synchronizing stream, creating cipher 1. The other output, they're going to take a portion of that XOR process, and that's fed into the next block here, use it as the initialization vector, then that then gets encrypted and then streamed with block 2, and that process goes on forever. So what you really need to know about cipher feedback is that it's a self-synchronizing stream cipher, and it takes the current block output of the XOR process and is using that as the initialization vector. The definition would be a self-synchronizing stream on the blocks where the initialization vector is encrypted and XORed with the data stream. Output feedback is almost the same as cipher feedback mode. It generates this initialization vector, which is then encrypted with an advanced encryption standard or any encryption algorithm. And however, the difference is it takes that output from the cipher stage and uses that as the initialization vector for the next set of data, while the other portion of the output continues to get XORed, and because it's a stream one by one with this block 1, creating this cipher 1, while the output over here from the cipher stage is used as the initialization vector. Now the cipher mode, the counter, that is when it's converting a block into a stream cipher, but it's using a counter value and a nonce. A nonce is a random number that's generated once. So with block 1, the counter starts at 0, and then for each additional block, the counter just keeps raising by 1, and each block is going to be completely independent of each other, allowing for parallel processing. So when the hardware is receiving all of this data, if you have multiple processors, it's able to decrypt that information a lot faster. Pretty good privacy, that's a software package that allows users to send encrypted and authenticated emails. That software package encrypts emails and authenticates them. You have to know that. Stream encryption, that's when bits are encrypted one at a time, and it's a lot faster than block encryption, and it's used typically for like real-time applications such as satellites, wireless, phone calls. RC4 and Cha-Cha are stream ciphers. Block encryption. That's when data is encrypted in fixed block sizes such as 128, 192, and used for like data at rest, file encryption, and data communication. Block encryption algorithms, symmetric examples are Camellia, Triple Des, Twofish, Blowfish, RC2, AES, IDEA, DES, XDEA, and Skipjack. And a memory technique that I like to use is C32 braids excess. And so you're going to be like, oh, see, there's 32 braids and there's an excess of them. Okay? Modes of operations that you typically see are electronic codebook, cipher block chaining, cipher feedback, output feedback, and counter mode. Now with these block sizes, you have to know the block size, the key size, and how many rounds there are in those encryptions. Today we're going to look at the initialization vector and the benefits it has with the ciphertext. So one of the major issues is a playback attack where you're copying an encrypted message and then playing it back, and the same plain text message is given every single time. So adding the initialization vector or nonce value changes the output from block to block or frame to frame. That way, if the input is the same, it's always going to have a different output because of this initialization vector or the nonce value. Initialization vector is a random value / seed is another term that they use for it. And it always must be sent with the ciphertext in 99% of cases. Let's see here. With the substitution bytes, SBox, you need to know that substitution is referring from a process of replacing one value with another value based on a predefined mapping or a lookup table. So the substitution byte SBox, that's used with advanced encryption standard, and depending on what the input is, it's going to output one of these different values here. Shift row transformation, that is another encryption technique or transformation technique providing diffusion, and it's spreading the input data across multiple rows and columns of the state of the matrix to create more randomness. So with the shift row transformation, the first row stays exactly the same, and then the second row moves by 1 byte to the left. So if it's on the far left of the data, it moves over here. Okay. The second row is the third row has a 2-byte circular left shift, so 5A is moving all the way over here, and let's see here, D5 is moving over here, so it's just 2 shifts. With the fourth row, that's a 3-byte circular left shift. All right. Now, what's really important is you understand the meaning of diffusion, which is a small change in the input data creates a significant change in the output data. So with padding, there's 6 different types, and it ensures that the message fits into the block size, and you can do that through the bits, null values, which is just all zeros, random bits, which is either the 1 or 0, and it helps mitigate from intruders analyzing the end blocks from patterns. So DES, that uses a 64-bit block size and a 56-bit key size and 16 rounds. The 8 bits that are missing here are used for parity, and parity bits are used for error detection. Triple Des, it's a 64-bit block size and a 112-bit key size and 48 rounds. So it uses 2 keys and 3 executions of the Des algorithm, which is why it has 48 rounds compared to the previous of 16 rounds. Today we're going to take a look at entropy, which refers to the amount of randomness or unpredictability present in the cryptographic key, and it really measures how difficult it would be for an attacker to guess or derive the key from a brute force or cryptanalytic method. Because many password systems and operating systems base their encryption keys on a passphrase, Even though that they use very strong encryption, passwords that protect them are open to dictionary attacks and overall randomness will be low. So encryption and decryption, the best and most simple definition for that is that encryption is the process of converting plain text into ciphertext, and decryption is the process of converting ciphertext to plain text. Encoding and decoding, that refers to the process of converting data from one form to another form. And you'll see that's often used like in the terms of data compression, transmission, or storage. With Advanced Encryption Standard, it's the current standard for symmetric encryption. It's recommended by the NIST, or the National Institute of Standards and Technology. They also recommend a few different encryptions, but AES is the most widely used you'll see in the USA. The block size is 128 bits, and then it has three different key sizes of the 128 bits, 192, or 256 bits. And then you'll see with those rounds, there's the 10, 12, and 14. And the key size of 128 matches up with 10 rounds, 192 means 12 rounds, and the 256 matches up with the 14 rounds. And those rounds is referring to like transformation, substitution, and all the mathematical operations that it processes. So the more times it rounds, the more randomness the output, and the stronger the encryption. Here are all the symmetric block encryptions and the memory technique of C32 braids excess. Like, see those 32 braids, and there's an excess of them. IDEA. IDEA is a 64-bit block with a key size of 128 bits, and then it has over 17 rounds, and it's free to use in non-commercial applications. And then there's RC2, RC5, and RC6. So each number is an improved version of the encryption. So RC2 versus RC5. RC5, the encryption is going to be a lot stronger, and then RC6 was an improvement over RC5. And then you can see all the different block sizes. RC2 having a 64-bit block size, a suggested minimum of 40, it's 18 rounds. RC5, a block size of 32, 64, 128 bits. A key size ranging anywhere from 0 to 2048, that's a typo there, and rounds anywhere from 0 to 255. The RC6, that has a variable, but it's common for 128 bits, and then the key size is variable, but commonly you'll see 128, 192, or 256 bits for that key size with a round of 20. So with Skipjack, that is a block size of 64 bits and a key size of 80 bits with 32 rounds. Now, the National Institute of Standards and Technology no longer recommends this encryption. It was used on a Clipper chip used to secure voice and data transmissions while allowing government to decrypt the communications if necessary for law enforcement purposes. Here's all the symmetric block encryptions, and a memory technique to help remember those is C32 braids excess. See those 32 braids? There's an excess, like there's an excess amount of them, okay? C32 braids excess. Blowfish and twofish. These are symmetric block encryptions. Blowfish has a 64-bit block size, a key size anywhere from 32 to 448, but common 128, 192, 256 with 16 rounds. Twofish, well, double, so it has double the block size. Recommended sizes 128, 192, 256. Same amount of rounds. It's a general purpose private key encryption. It's also Blowfish was unpatented, so anybody can use that. Here's all these symmetric encryption algorithms. Camellia. Okay, so Camellia was invented by Mitsubishi and NTT. I also want to point out that it's not Mitsubishi, the car brand. It's Mitsubishi Electric and Nippon Telegraph and Telephone Corporation. Extia, that's pronounced extended T. And here are the block size. Extia has a 64-bit block size, a key size of 128, and variable amount of rounds, suggested 64 rounds. With Camellia has a 128-bit block size, key size 128, 192, 256 rounds, 18 or 24. So with hashing checks for integrity, and if any of the contents were changed, then the output's going to be completely different, even for the most microscopic thing like a space or one letter. Now, there's a few different techniques, such as the base64, which is used for email, and Unix password hashing. It's contained in the password file. For Windows systems, it's stored in the system registry, and they use the NT password hashing or NTLM. The main techniques continued are also MD5, that's 128 bits or 32 hexadecimal. So this is 32 characters right here that can be converted to text format. SHA is 40 hexadecimal output, which is placed here, or 160 bits. And then SHA-2, you can have 256, 384, or 512-bit signatures. Also, I wanted to comment that a digital fingerprint is also known as a hash value or cryptographic hash. That is just another term that they use. So with a hash collision, that's when two different inputs produce the same hash signature. So for example, there's a document 1, and that says the house is great, and you put it through this MD5 algorithm, and you have a certain output. Now with document 2, it has completely different contents, although when you put it through the MD5 algorithm, somehow it has the same exact hash output. That is considered a hash collision. Now, a pre-image attack, this refers to finding that input that corresponds to a specific hash output produced by a cryptographic hash function. So this one is an attack because it's on purpose. The similar context, that's where part of the message has significance to the original and it generates the same hash value. That term is a pre-image attack. Now, the full context, that's where an alternative message is created with the same hash signature and has direct relation to the original contents. This is an extension of the pre-image attack. A birthday attack. This is a type of attack based on the birthday problem in probability theory to get those hash collisions. So let's say there's 70 people in a room. This is how you explain the birthday theory, by the way. So there's 70 people in a room, and there's a 99.99% chance two people are sharing the same birthday. So using this method, the same hash value of those two files would require 2 to the m squared of random messages created to have the same hash value. So why this is dangerous is that, well, hashes are used for integrity verification, digital signatures, and password storage. So what could happen? Well, with forged signatures, they could be used to impersonate a legitimate sender. With passwords, they could be used to gain access to those unauthorized systems. With data integrity, well, where hash values are used to verify the data integrity, make sure nothing's changed, the collision can exploit that and tamper the data and completely change it, and you wouldn't even know because it would go on undetected. So salt, that's when you add random characters to a password before it's hashed. Now this stops passwords from having the same value from being cracked, because if two people have the same password, let's say it's monkey and the other person has the password monkey, the salt is going to add additional characters, and then when it's put through that hashing algorithm such as SHA-256 or bcrypt, which is specifically designed for passwords, it's going to output completely different from each other, even though the password is the same. So the salt value associated with each user's account is typically constant and remains the same for that user. So what that means is that when you generate a password online and that salt is randomly generated, that randomly generated salt is now associated with your password, and so each time you log in, you get that same salt or that same randomness added onto your password and then hashed. And a weakness of that is that the salt is stored next to the hashed password, and so whenever you update your password, you do generate a new salt value. Example of what I was just telling you. So user registration or password update. When a user registers for an account or that updates their password, a new random salt value is generated, specifically only for that user. Now, the random salt value is then concatenated with that user's password and then combined and stringed is hashed using a cryptographic hash function. This hash function, along with the salt, is stored in that database. Now, for authentication, when the user attempts to log in, the salt associated with their account is retrieved from the database. Now, hashing for authentication. The retrieved salt is then combined with the user's provided password, and the resulting string is hashed using the same cryptographic hash function, and this new hash value is compared with the stored hash password. Now, if the hash value matches the stored password, then the authentication is successful. Bcrypt. Bcrypt is a hash generator for passwords that adds salt to the passwords and then hashes them. It's specifically designed to be used only with passwords versus a general purpose hashing algorithm like MD5 or SHA. You can use that with many things, but Bcrypt specifically designed for passwords. And what it does is it adds salts to the passwords and then hashes them. So with a rainbow table, that's where they're taking a mapped hash value to the original plaintext value. It's typically an offline attack, and how this typically works is that you log into a website such as Amazon.com, and it takes your username and password. A company, they don't want to store your password in their database because that's risky if someone were to break in. So what they do is they salt that password and then they hash it with a hashing algorithm, or they use something like bcrypt that salts and hashes the value. Now, the hash value is stored in their database, and so the rainbow table is assuming that they've already broken into that database and then downloaded it onto their computer. Now they're taking their pre-computed list, which is the rainbow table of hash values, and comparing that to the hash values that they've stolen of that database. And they're looking to see if they're able to map that to a plain text, to be able to log into one of these systems with your username and password. Salting, it can be an effective way to mitigate against rainbow attacks, but it doesn't guarantee that. Now, the hash message authentication code, that is referring to the integrity and authentication of a message, and it involves hashing the message with a secret key, and it's a little bit different from the standard hashing method. It's a purely one-way method function, and again, it involves hashing the message with a secret key. Now, Apache Password Recovery 1, APR1 is a hashing algorithm used for generating password hashes, and it uses MD5 and hashes that value about 1,000 times. It is configurable, and to slow down the attackers. So it just keeps hashing the hash value 1,000 times. So it's a very slow process. So with LDAP, LDAP is the Lightweight Directory Access Protocol, where entities are mapped to a global infrastructure. So what exactly does that mean? Well, let's say you log into your computer for the first time. LDAP is going to map your information to your profile within the directory services, such as Active Directory. And when you go to work the next day, if your computer's not working, you can use the computer next to yours because it's going to pull your information and your profile from the directory services, such as all the group policy objects of what you can and can't access. And really, it's bridging that communication and mapping your profile to the global infrastructure so you can use any device. Now with PHP Pass is the portable PHP password hashing framework, and it's a PHP library. So PHP is a coding language, and it's designed for secure hashing and storage. Cisco hashes. So Cisco devices usually consist of like routers, switches, firewalls, and security appliances. And it's going to store all of your passwords using different types of hashing algorithms. And so originally they used type 5, which is a weaker hashing algorithm. And then they use type 7, they use a Vigenère. And then now they're using the PBK-DF2, and it's a lot stronger hashing algorithm. So with PBK-DF2, or password-based key derivation function 2, it salts the password and then it hashes that value over 1,000 times. That is configurable, and it's a slow process. Now, it's used in WPA2 to make the brute force attacks more difficult and time-consuming, and it was used in TrueCrypt, which encrypt the hard drives, but that's now deprecated. So a non-cryptographic hash, it allows for low processing power. So they're both hashes, but this is a lower processing power. It's fast and can be run on most computers. The negative is that it's easily broken, and hashes are supposed to be non-reversible. So examples are Spooky, Bernstein hash, DJB2, Java hash the code, and hash. Password strength. So the number of characters in the password and the range of characters or combinations. So a 7-character password is going to take about 11.9 days to crack on 1 million password attempts per second. Now on a 10-character password, that could take 4,000 years because the results are just exponential as you increase the length of a password. Now, with cloud cracking, that's referring to this NVIDIA CUDA architecture and using the cloud capabilities such as Amazon Cloud or Microsoft Azure and their processing powers to be able to distribute the workload across multiple machines to accelerate the attack. So CBC MAC and CCM, that's counter with cipher block chaining and message authentication code. It's going to add authentication to the encryption of AES because AES encryption does not automatically come or provide authentication. And so it's going to verify the person is who they say they are, that they sent it, and the integrity of the data has not changed. In Windows hashing, so computers that are connected to an Active Directory domain, they natively use the NTLM version 2 to hash those passwords, and they're stored in the Active Directory database. And often, John the Ripper and OPH crack are used to crack those hash versions in the LM and NTLM. Now, Linux hashing, the main methods would be bcrypt, that's salting and hashing, MD5, crypt1, SHA-1, SHA-256, and the SHA-512. So the Linux hashing covers the bcrypt and all the SHA types. Now, typically, all the passwords are stored in the /etc/shadow file. In the 1980s, it was the etc/password. Today, we're going to take a look at public key infrastructure and then digital signatures. So a public key infrastructure stores all the public keys and is trusted by all parties. So if you work in a company, each employee will have a public key that is stored in the public key infrastructure. So if employee A wants to send employee B an email, their system's going to reach out to the public key infrastructure, it's going to grab employee B's public key, and it's going to encrypt that email with employee B's public key. Now, when employee B receives that email, they're going to decrypt it with their private key. So in summary, it's encrypted with employee B's public key and then decrypted with employee B's private key. Now, the public key is widely distributed and can be freely shared with anyone. And for the PKI, it's used for encryption. It's a one-way formula or asymmetric. The private key is kept secret and known only to the key's owner. It's used for decryption. So example 2, the sender will encrypt the email with the receiver's public key, and then the email will be decrypted with the receiver's private key. So digital certificates. So digital certificates is when a signer digitally signs a document, and that document has a cryptographic hash. So it takes all the document, all the contents, and it runs it through a hashing algorithm such as SHA-256. Now that hash is generated for the document, and it's encrypted with the signer's private key. Now, when you send that digital signature out on that document, the receiver is going to verify your identity with the public key. So the recipient can decrypt the encrypted hash with the sender's public key. A cryptographic hash is again generated on the recipient's end, and it matches for authenticity for the original hash that was created on your side, and then when they receive that email on their side. So it's signed with the sender's private key and then decrypted with the sender's public key. So it's almost the exact opposite of public key infrastructure, because when you're encrypting an email, you encrypt it with the receiver's public key, and then the receiver decrypts that email with their private key. But if you also digitally sign that document, you're going to sign the document with your private key, and then they're going to decrypt that signature with your public key. So here's an example. A business wants to digitally sign a certificate and send it to a customer. The business digitally signs the certificate with their private key. So whenever you're signing, it's always done with the private key, and whoever's signing it, it's their key. The customer will then verify their identity/signature with the business's public key, because it's the business that is signing it and sending it out. Example 2. A certificate authority wants to digitally sign a certificate and send it to a business. So the certificate authority will sign the certificate with their private key, and then the business will verify their identity/signature with the certificate authority's public key. So in summary, the sender signs a certificate with their private key, and their identity is verified with their public key. So public key infrastructure and digital certificates. So we're going to take a look at the conglomerate example. Employee A wants to send employee B an email, an encrypted email, and also digitally sign it. So employee A will encrypt the email with employee B's public key. Employee B is going to decrypt that email with their private key. Now, the email is also digitally signed with employee's A private key, and the email signature is decrypted with employee A's public key by employee B. Now we're going to take a look at a little bit about the process here. And when the computer receives an encrypted email that's also digitally signed, the first step it does is verify the digital signature, and then it decrypts the email. So digital certificates. A digital certificate is a digital document issued by a trusted entity known as a certificate authority or certification authority. The purpose of a digital certificate is to bind a public key to an individual device or service or person, for example, within the company. The digital signature on the digital certificate provides a way for others to verify the authenticity of that public key. Public key infrastructure in the CIA triad relation. So anytime you get a question with confidentiality, that's referring to encryption. And with encryption, you're going to encrypt all the data with the receiver's public key, and then they're going to decrypt that with their private key. If you get a question with the integrity portion of the CIA triad, which is hash, integrity, non-repudiation, so if the question in the Security Plus says any of those three words, it's referring to a digital signature, which is signed with the sender's private key and then decrypted with the sender's public key. So key verbiage, if it says hash, integrity, non-repudiation, they're referring to digital signature. It's signed with the sender's private key and then decrypted with their public key. So public key cryptography standard number 5 is used for password-based encryption. So it provides a framework. It doesn't define the format. So an example would be you're adding salt to a password and then hashing it, but it's not defining like how you're implementing the salt and which hashing algorithm you're using. Public key cryptography standard number 7 is used to sign and encrypt messages in a public key infrastructure, and it allows for the creation and verification of digital signatures. Public key cryptography standard number 10. That is a standard format used for requesting digital certificates from certificate authorities, which is also another term for a certificate signing request. That's when the entity or end user is requesting a digital certificate, reaches out to the public key infrastructure, and that's a certificate signing request. Public key cryptography standard number 12 is used to bundle a private key with its X.509 certificate or to bundle all the members of a chain of trust. So it's specifying the format for storing and transferring the personal identity information, including private key certificates and other related information. It's used for exporting and importing the certificates and private keys. So it's bundling all that information together into a single encrypted file format. We're going to take a look at what they mean by a chain of trust and the certificate authority hierarchy. So a certificate authority hierarchy is a structure. Here we can see the root certificate authority, and it's interconnected with these intermediate certificate authorities. So this is the original certificate authority, and then you set up the additional certificate authorities that actually issue the digital certificates. Now, in a enterprise environment, a lot of the times you'll see them take the root certificate authority offline because if it's offline, then it can't be compromised. And when they want to update something, they just place it back on the network. All the devices recognize this as the root certificate authority. And if you want to update, it can go ahead and push that out, and then they take it back off to secure the system. The root certificate trusts the immediate certificate authorities, and the immediate certificate authorities can issue digital certificates to the end users, servers, devices, or other entities within the public key infrastructure. Any device that relies on a digital certificate or performs actions with certificates validation or verification is interacting with the public key infrastructure in some way. So with the one-way client or server authentication, one side is proving their identity to the other service. With the two-way authentication, both the client and the server are identifying themselves to each other, and that's more secure. Now, they can do this in different ways. There's the end-to-end authentication. So that's when the initial entry point or communications, they verify that they are who they say they are, and there's going to be no more checks. With the intermediate authentication, not only do they check on the initial entry point, but there's multiple different stages within the communication that they are verifying who they say they are, so the intermediate authentication is a little bit stronger. Now, the types of authentication, there's something you know, such as a password or PIN, something you have, a smart card or token, something you are, a fingerprint, facial recognition, geolocation. Sometimes you'll see the term as geofencing because that service or network will only work if you're in that geofenced location. Something you do, that could be like your gait of how you walk. And I also wanted to point out that a digital certificate is something that you have. So there's many different types of digital certificates, such as the IKE, Public Key Cryptography Standard number 7, 10, the X.509 certificates. Now the information that's contained on those certificates is the public key, the issuer's name, the start date, end date, the subject, the certificate revocation list, and the online certificate service providers. I'll have the certificate chains, the thumbprint algorithm, such as the MD5 or SHA-256, and then it'll have the thumbprint hash value. Now, the stages of the key certificate management. This is very important. Okay, the initialization, that's going to cover the registration, the key pair generation, certificate creation, and certificate key distribution, the certificate dissemination, and key backup. So when you're on Amazon and you create your key pair for the first time, you save your private key onto your computer and then you send Amazon your public key. And so they only have that. Now the issued, that covers the certificate retrieval, certificate validation, key recovery, and key update. Now cancellation, this covers key expiration, certificate revocation, key history, and key archiving. Now the main states for revocation. So either the certificate has been revoked and it can't be reversed, and that often occurs when the private key has been breached or when the certificate trust is on hold and that can be reversed. So they would place a certificate on hold if there was a possible breach, but they're not 100% sure. But they don't want anything to work in case if it was. And now if that investigation found that nothing was wrong, then they'll go ahead and reactivate that certificate. However, if it was compromised, then they're going to completely revoke it from there. So in tunnel mode, the entire packet is encrypted and even the IP address. So they need to place an additional IP address in front. That way it's able to reach its destination. So how this process works is that this user here, let's say they make an internet connection, and now that internet connection all the way to the gateway router is in clear text. So everybody can read the message, the contents. And as it gets encrypted at the gateway router, that's where it adds on that additional IP address, and the first IP address is encrypted with all the data. Now, when it goes through the internet, none of these users are able to read the content. They don't know the destination or end device. They can see the first IP address, but they don't know the destination. Then it reaches its destination local area network, and this gateway router has 2 associated IP addresses, and it knows when it receives a message from this IP address to rip off that first IP address and then start to decrypt that packet, and that way it knows where to send this internet connection, which is going to user Y. So as it's passing through this local area network, all of this traffic is in clear text, or all the users are able to read this traffic. Now in transport mode, it works a little bit differently. The connection gets encrypted at the end user all the way to the other end user. This is where it gets decrypted. So as it's passing through the entire local area network, none of the users on this local area network are able to read that traffic. Now, the attackers here, or anybody that's just snooping around and reading these internet packets, these IP packets, are able to see the destination, but they still don't know the contents of that message. This is assuming that it's an ESP, encapsulating security mode, which I'll go over in the next slide. So, transport mode, ESP, it's encrypted from end user to end user, and nobody is able to read the traffic except for the end user. So authentication header, that's when it provides integrity and authentication, and it only provides integrity and authentication. So in these last two, tunnel versus transport, everybody would be able to read everything from tunnel or transport if they use the authentication header. But it would let the end user know if any of the information was changed because it provides integrity and authentication. Now, the encapsulating security payload, those are the two I just showed you with the transport and tunnel, because it encrypts the entire packet and it provides integrity with authenticity. You need to know that ESP uses protocol 50 and that authentication header uses protocol 51. So here's how authentication header works. It has the IP address, authentication header, and all of this is in Cleartext, just like in tunnel mode. So everyone's able to read everything. Now with the ESP mode, in the transport mode, here you have the IP address, and only this portion of the data is encrypted. However, in tunnel mode, you see that the IP address is encrypted all the way through the data, and then here's the additional IP address that they put in front that everyone's able to read. And the quick summary of transport versus tunnel, that transport mode encrypts the payload at the end device while leaving the original IP header intact, and tunnel mode encapsulates and encrypts the entire original IP packet at the gateway router or firewall. So it's gateway router to gateway router, and transport mode is end device to end device. With a IPsec security connection, there's two main phases. The first phase defines the internet key exchange where the hashing method and the encryption keys are defined, and then the second phase, which defines the policies to be used in the tunnel. So those policies or protocols are ESP and AH. They can be used either separately or they can be put together. Now the ESP works on protocol 50, and only the host at the other end of the IPsec tunnel can decrypt the contents of the data packet. ESP does have a weakness of replay attacks, and then the AH, or the authentication header protocol, is on protocol 51, and that provides complete authentication in a packet and has a mechanism of sequence numbers to prevent the replay attacks. So internet key exchange is a protocol used in IPsec. It's used for tunneling and to negotiate the security parameters, exchanging cryptographic keys, and establishing the secure tunnels for encrypted communications. And you really need to know that it uses UDP port 500, because if your firewall is blocking that port, then that connection is going to fail. And so you have to make sure that UDP port 500 is open, and so that it can establish the tunnel and negotiate those security parameters. Here are the internet key exchange phases. If you're interested in this, go ahead and pause the video. The onion routing. So the Tor network, also known as the onion router, is a decentralized network of volunteer-operated servers, nodes, that enable users to browse the internet anonymously and access websites and online services without revealing their identity or location. So it's designed to protect your privacy and anonymity by routing their internet traffic through a series of encrypted relays, thereby obscuring the IPs. So each relay, or the device that the communications that it's sending to, only knows the previous location where it was sent to. So if there was 5 relays, the 5th relay doesn't know the first location. It only knows the location of the 4th relay, and the 4th relay only knows the 5th relay and the relay behind it. So that's how it obscures your IP address and prevents network surveillance and censorship. So with key escrow, that's when the encryption keys are stored with a trusted third party, and it's usually given to law enforcement or government agencies in case if there's a legal case or investigation and they need to be able to access those systems. So a NOBUS backdoor, that is a mathematical way for government to crack encryption, but nobody else can. And so that term came from when they were creating some of these encryption standards and ways to implement encryption. They were first even stronger. However, the government didn't want them to be so powerful that they weren't able to crack them in a timely manner. And so that's why it's at a point where they call it the NOBUS, where a normal person won't be able to just crack those encryption codes, but the government would be able to. Now, AES, that's free from major vulnerabilities, but poor implementation can lead to problems. So with crypto cracking, there's the exhaustive search. That's when you're using a brute force to decrypt the ciphertext, trying every possible key. Now, the known plaintext. That's when the intruder knows part of the ciphertext and corresponding plaintext. They use the known ciphertext to decrypt the rest of the ciphertext that they don't know. Now, in the man-in-the-middle attack, that's when the intruder is hidden between the two parties and they impersonate one or both of them. And so if the network communication, they're intercepting here as it's traveling, and they're modifying that data, pretending to be this side or this side. or both. Now, the chosen ciphertext, that's when the intruder sends a message to the target, and that is encrypted with their public key, and the intruder is able to analyze the message, so they have access to where they're sending it to. And here are the steps here. Now, with crypto cracking, an active attack, that's when the intruder inserts or modifies the messages. So the man-in-the-middle attack, that would be classified as an active attack. Now, with the replay attack, that's when the intruder takes a legitimate message and then sends it into the network at some future point. So an example of that would be, let's say you're connected to your Wi-Fi from your computer to your router. Now, those Wi-Fi signals, how the attacker would do it, they would jam that signal, and then they would unjam it. And then your computer would resend the authentication to be able to connect to the router, and the attacker would intercept that, and then at a later point would send your legitimate authentication credentials to access the router credentials. And so that would be a replay attack. They're taking that legitimate message and then sending it later at some future point to be able to access the network. And then there's the cut and paste attack, time resetting, a time attack, and the RSA cracking. The RSA uses a 768-bit key, and it's attacked using the factorization of modulus. So lightweight cryptography, that's used for things with Internet of Things, RFID devices. Conventional like AES or SHA, it takes up a lot of processing power and too much space and a lot of battery power. So devices that are refrigerators or sensors underneath the ground or embedded systems, they need to use a lightweight cryptography, which is why the encryption is faster. It doesn't take a lot of processing power, but it's not as secure versus the conventional cryptography methods on these servers and desktops. So Bitcoin is a publicly available ledger of transactions known as blockchain. And publicly available ledger, that means anybody can go look up those transactions and see how the Bitcoin was transferred from one person to another. The first transaction ever mined was 50 Bitcoin, and there was a limited amount ever created. So Bitcoin is slowly released and it's mined through complex algorithms, and the rewards are reduced over time because currently the mining reward for each block is about 6.25 Bitcoins, and it's halved approximately every 4 years. Now, transactions are confirmed in about 10 minutes. And what that is referring to is if I trade or give away my Bitcoin, all the miners are the ones that confirm those transactions. Now, first, the receiver sends their public key, so that's the person without the Bitcoin, and the sender signs that transaction with their private key. So the person giving away their Bitcoin, they sign it with their private key, which is a 256-bit hash, and then they add their public key to that blockchain. Now that is captured by miners and they compile a list of all the transactions. Now the miner that successfully creates the blockchain and compiles a list of transactions is rewarded with the Bitcoin. So that's why there's an incentive for the miners to confirm these transactions as well. So they have two ways to earn the Bitcoin: confirm the transactions and also mine the Bitcoin. And because these blockchains just keep getting signed by these 256-bit hashes, the blockchains just keep getting larger over time, while the rewards for mining this Bitcoin was originally at 50, but is now at 6.25 Bitcoins. Now, Ethereum. After the hack, there was a split between what they called Ethereum Classic and Ethereum. Now, within Ethereum, we define the concept of gas, and that's used to measure the amount of work that is required to perform a single KICKAC 256 hash. Now, Ethereum transactions do have a fee associated with them. And so what's very important about Ethereum, that there's two versions: the Ethereum Classic, which is the original version, and the Ethereum. Today we're going to be learning about WEP and WEP plus TKIT. So WEP stands for Wired Equivalent Privacy, and it's one of the older security protocols that they use to secure the Wi-Fi network. It uses an RC4 stream cipher encryption, and that's in bold because that's important to remember, and it uses a 24-bit initialization vector and a bit key size of 40 bits. It has no protection against replay attacks, and a replay attack is when an attacker captures that transmission and later resubmits that data to pretend like they're an authorized source or to gain access to another device. It has no tampering identification, and then frequency analysis was used to reveal the original messages and break that encryption. One key factor is that it uses a global key for the whole network. So if you get access to that global key, you can read everything. Now TKIP was added onto it to improve WEP. So now they call it the Wire Equivalency Privacy WEP plus TKIP, Temporal and Key Integrity Protocol. So when they added TKIP, it increased the initialization vector to 48 bits. And what was really special about it is that it hashed the initialization vector and the secret key to create a special key that is then fed into the RC4 encryption with the initialization vector. So it uses a session key, and that key is never passed over the wireless network. It incorporated improved message integrity check to protect against bit flipping attacks identified in WEP. So RC4 is a stream cipher. It was designed by the RSA and it's very fast. It uses one transformation round and a variable key length from 1 to 256 bytes, or that's 8 to 2056 bits. 40-bit minimum is recommended. Now, with WEP, it used a 40-bit key size and a 24-bit initialization vector, and then RC4 encryption used a 128-bit key with WPA and a 40-bit initialization vector. Now, WPA did address some of the weaknesses of WEP, including the larger bit key size and a larger initialization vector going from 24 to 48 bits. But the other things that it introduced was the pre-shared key, which everyone uses the same password, is what a pre-shared key means, such as at your home. Everyone uses the same password, or at the coffee shop, everyone uses the same password. Now, in Enterprise, it uses authentication server, so that's WPA Enterprise. So everyone has their own username and password. It uses 802.1x and EAT and supports TKIP with a session key. Now, WPA2, this is one of the newer wireless standards that they have out. It's 128 bits with the 256 AES CCMP. It's backwards compatible with WPA, and it supports a pre-shared key or enterprise. Now, the wireless protocols, these are PEEP, which supports authentication for server-supplied digital certificates, EAP TLS, this supports client-provided digital certificates, and LEAP, that supports username and passwords, which is now deprecated. So Cha-Cha-20, this is a stream cipher proposed by Google, and it has 20 rounds. That's why they call it Cha-Cha-20. Now, it's an alternative to AES. It's 3 times faster than the software-enabled advanced encryption standard, and it's not sensitive to timing attacks. It's using TLS connections. Again, it's a stream cipher with 20 rounds. Now, A5 ciphers, they use these for mobile communications and mobile networks. And the stream ciphers, originally A5/2, they kept it intentionally weak so that nation states can crack that cipher. And the A5/1, it's a little bit stronger. And now with the LTE, they use the A5/3 cipher method. Today, we're going to take a look at this practice test and talk about why the answer is the answer and what the other options would match up with. Question number 1. A certificate authority wants to sign a certificate and issue it to Wolf Industries, a business. Which key will they use to sign the certificate? So anytime a certificate is signed, it's always signed with the private key. And since the certificate authority is signing the certificate, it's going to be the private key of the certificate authority. If the Wolf Industries was signing this certificate, then it would be signed with Wolf Industries' private key. So I want to talk a little bit about how this process works. So when a signer digitally signs a document, let's say there's an email, a cryptographic hash is generated for this document. Now, that hash is then encrypted with the sender's private key, and then they're also going to provide their public key with that document so you can verify they are the person that they say they are. But the process of a certificate is not encrypting the rest of the message. It's only encrypting that hash value, and so you can verify that the person is who they are, that they say they are, that's sending it. So question number 2, when the certificate authority wants to prove their identity, which key will they provide to prove their identity? They would provide their public key. So they'd sign their certificate with their private key, and then they would provide their public key. If Wolf Industry was giving this out to customers, they would sign their certificate with their private key and then use their public key to prove their identity. Question 3. What should an administrator use to sign and encrypt messages for the public key infrastructure? So PKCS, that stands for Public Key Cryptography Standard. And number 5 is used for password-based encryption. Number 7 is used to sign and encrypt messages for public key infrastructure. So that's the answer. Number 10, a standard format used for requesting digital certificates from certificate authorities. Number 12. Number 12 is used to bundle a private key with its X.509 certificate or to bundle all the members of a chain of trust. So when they use a certificate, it's for server authentication, client authentication, code signing, email signing, timestamping. And here's some common types of certificates that they have. Question number 4. Which field shows who created the certificate in X.509 certificate? The subject has a little bit about the subject of the certificate. The issuer shows who created the certificate, the version, such as the version number, and the thumbprint, which is a unique value and hash of the certificate. And so when you think of a thumbprint, I want you to something that is unique to you, and that's why they call it a thumbprint, because a hash value is a unique value. Here's some of the contents that they would have on a certificate. The public key, the issuer, serial date, always has a start and end date, subject, thumbprint algorithm. Question number 5. Which certificate management process involves certificate creation and certificate key distribution? So we're going to take a look at all the options on here. So initialization includes registration, key pair generation, certificate creation, certificate and key distribution, which is the answer, certificate dissemination, and key backup. So issued is certificate retrieval, certificate validation, key recovery, and updating. Cancellation, that would be used for certificate expiration, certificate revocation. So perhaps there's some sort of compromise where they wouldn't want to cancel those keys so they no longer work. Key history and key archiving. A hold, well, you would utilize a hold when there's a possible security incident, but you're not sure. And so you want to temporarily disable those keys. And if it's a false positive and everything is good, then you can go ahead and reactivate those keys. If there was something malicious, then you can go ahead and cancel those keys so they no longer work. And so if you've ever been to a website and it says, do you trust this source? Like the certificate is no longer valid. Well, there could be a number of reasons why. Perhaps that their certificate expired, or maybe those keys were revoked from that website. Question number 6. What is the first step for obtaining a signed digital certificate signed by a trusted certificate authority? So the first thing you would do is you would generate a key pair, and then you would provide the public key to the certificate authority. Or another example is that if you are setting up your Amazon cloud, you're going to create your public and private key. You're going to store that private key on your computer and then provide the Amazon cloud the public key. And now if you lost that private key, you would not be able to retrieve it because Amazon wouldn't hold on to your private key. Then the next thing regarding this question, like the certificate authority generates the digital certificate for the requester. And then they would sign the digital certificate with the certificate authority's private key and issue that to the requester. And this would be the first thing that the certificate authority does, is they're going to sign that certificate with their private key. This would be the first thing for their requester that they would use. Question number 7. Which algorithm would you use to encrypt an email? We have MD5, SHA-1, SMIME, or AES. So anytime that you see MD5 or MD and HA, I want you to think hashing algorithm. So HA stands for hashing algorithm, and the MD stands for message digest, which is the earlier form of a hashing algorithm. SMIME is the correct answer, and SMIME is used for sending digitally signed and encrypted emails or messages. And AES is a encryption type, but specifically the best one here would be S-MIME. Question number 8. Which way can encryption keys be distributed securely? So the best way here would be from Diffie-Hellman. Diffie-Hellman uses asymmetric formula to go ahead and get the symmetric encryption set up. So Diffie-Hellman is used to distribute keys. So initially when you're logging on through an online website, the first time it's gonna be the asymmetric encryption, and what it tries to do is then establish the symmetric encryption typically, which is better for bulk transfer of data. And then the other option on here is MD, which stands for message digest, which is for hashing, and hashing is not encryption. Hashing is for integrity, and RTF, that stands for rich text format, which is not covered. Question number 9. What is the role of symmetric encryption in encryption and decryption? So for symmetric encryption, both the keys are exactly the same. So the secret key is the same one used for encryption, and it's the same key used for decryption. Let's take a look at why this is definitely not the right answer. A public key is used for both encryption and decryption. Well, you would never want to use a public key because public means everybody has it. And so you're not going to use that. That's not a valid answer at all. On the third option here, we have a public key is used for encryption and a private key for decryption. So what this is referring to is asymmetric encryption. And so if I want to send you an email, I'm going to go ahead and encrypt that with your public key, and then you're going to decrypt it with your private key. The public key infrastructure holds all the public keys. So if you're in a company, it's going to hold all the public keys of all the users in that organization, and whenever you want to send someone else an email, your system is going to retrieve their public key, and then only that other user that you're sending it to, they're going to decrypt it with their private key. And then when we're looking at signatures, you would sign that email. If you wanted to digitally sign that email, you would digitally sign it with your private key and provide them your public key. But for the encryption of the document, you're going to encrypt it with their public key, and then they're going to decrypt it with their private key. And the last option on here, determine whether two files are identical or not without knowing anything about their contents. That is referring to hashing. Question number 10. What is the purpose of a digital certificate? To validate the integrity and authenticity? No. To bind a public key to an individual device or service. So the answer is to bind a public key to an individual device or service. While on the digital certificate, the signature would validate the integrity and authenticity, so you can verify that the person is who they say they are that send it to you. And the other options, they don't work here. Question 11. What list maintained by a certificate authority that contains serial numbers of certificates that have been revoked? The certificate revocation list is what CRL stands for, and that is what contains the serial numbers on the certificates that have been revoked. CA stands for Certificate Authority. CP stands for Certificate Policy, which is a document that defines the rules and requirements for the issuance and management of digital certificates. A CSR, that's a certificate signing request, and that's generated by the entity that wants a digital certificate, and they send that off to the certificate authority that then can generate the digital certificate. Question 12. What is the key size of WPA, Wi-Fi Protected Access? That is 128 bits, while 40 bits, that would be for something used like with WEP. WEP stands for Wired Equivalency Privacy and is one of the original, if not the original, Wi-Fi protocols that they utilized, and that can be broken within seconds. Question 13. Where is the WPA personally typically implemented? So WPA personal, that stands for Wi-Fi Protected Access, and you would normally see that for a home network and coffee shops. So something that you would use right now for WPA personal in your home network, you're going to see it's going to have like a pre-shared key, or that means everyone uses the same password. While in a enterprise environment, you would see that as WPA enterprise, they're going to have a radius server, which is going to use for user authentication. So you're going to have like username, password. Each individual has their own setup. Sometimes there's additional ways to log in, such as a common access card, or something you are, such as a retina scan or fingerprint, and high security environments for WPA Enterprise. Question 14. Which cipher is used with WPA2? So WPA2, let's talk about each of the options on here. So RC5 is a symmetric key block cipher encryption algorithm that was later replaced by AES. AES, Advanced Encryption Standard Counter Mode with cipher block chaining, is used with WPA2. Typically, you see AES utilized in the government because it's considered um, widely the most accepted standard and typically the best. However, depending on the application, maybe a different encryption may suit the enterprise's needs. WEP is a outdated and uses RC4, which is deprecated in modern security practices. TKIP, that stands for Temporal Key Integrity Protocol, and that's a security protocol which uses Wi-Fi networks to enhance the security of data transmission. The improvement that it added was hashing the initialization vector and the secret key, but was also later replaced by AES. Question 15. Which best describes a replay attack? The answer here would be a malicious attack that intercepts a legitimate communication session to gain unauthorized access to a system. So what happens is that let's say a user has a legitimate session to an outside source over the internet, and the bad actor, they intercept that message and your credentials are that you use to log in by intercepting those packets, and later they try to resubmit that to gain access to that system. And that's why they call it a replay attack, because they're capturing that in the middle of transfer and then reissuing that to gain access. A radius server, that is used for authentication and authorization that manages user access to a network. TKIP, we talked a little bit about that on the last question. And then using a stream cipher, as it typically is much faster than a block cipher. While this is true, stream ciphers, you're going to see that typically for live streaming or anything like voice over IP, anything that is live and happening, versus a block cipher, which is typically for larger blocks. So block ciphers are used for like data at rest, file encryption, and data communication. That would be a better definition for that. Let's take a look at the next question. Question 16. Which picture displays a VPN using ESP tunnel mode? So first I want to talk a little bit about the VPN, which is a virtual private network, a technology that allows you to create a secure and private network connection over the internet. In the first image here, we have transport mode. So the data is encrypted in this packet here. However, the IP address, everyone's going to be able to see that as it travels across the internet. And versus the tunnel mode is, we'd pretend like this 8888 is right here. Well, that's encrypted. So all of this data is now encrypted, and it places another IP address in front of that. So it's another IP packet in front. And the reason it does that is that if anyone were to intercept this message, well, now they only know this IP address. So when it reaches the other side of the destination, that router rips this IP. Question 17. UDP port 500 is used for what? Let's take a look at all the options here. So SNMP trap messages, that's port 162, and is specifically used for traps or notifications that alerts the system if there's any sort of event failures or security breaches or other significant events to the NMS. The IPsec key exchange, that is port 500, and that's used for Internet Key Exchange Protocol. LDAP, that's port 389, and that's associated with Lightweight Directory Access Protocol. SMTPS, That is for port 465 and was previously designated for Simple Mail Transfer Protocol Secure, but that service is now deprecated. So the answer would be IPsec key exchange. Question 18. What best describes a protocol? Okay, let's take a look at the options here. A set of rules and conventions that governs how data is transmitted and received over a network. It defines the format of data packets, the order of data exchange, error handling, and other communication aspects. Yes, that is exactly what describes a protocol. The other option on here, a numeric identifier used to distinguish different services or processes on a single device within a network. Ports are used in conjunction with the IP address to route data to the appropriate application or service. So whenever your IP packet is sending out, it's going to have an IP address of, for example, 8888 colon, and then let's say a port of 53 for DNS. Question 19. Which cipher best describes a Caesar cipher? Let's take a look at all the options on here. Uses a grid to map letters into numeric values. That's a Bifid cipher, which is a classical substitution method and uses elements of the Polyalphabetic and Playfair cipher. Hashing algorithm, definitely not the answer. Each letter in the plaintext is shifted forward or backward in the alphabet according to the chosen shift value. That is a Caesar cipher. As for example, if A is being shifted 3 letters, it would go to D. And the last option on here, a keyword or phrase chosen by the sender and known to the recipient. It is a 26 by 26 grid of alphabets. That is a Vigenère cipher. Which best describes a Vigenère cipher? Well, we actually just looked at that answer there, and that would be a keyword or phrase chosen by the sender and known to the recipient. It's a 26 by 26 grid of alphabets. Let's take a look at the other options on here. We have the 5 by 5 matrix with non-repeating characters. That would be the Playfair. We have also known as a zigzag cipher. They're talking about the railroad cipher. Is a type of transportation cipher, rearranges the letters of a message to make it harder to read. The name rail fence cipher comes from the way the letters are arranged in a zigzag pattern that resemble a fence made of rails. And then the last option, shape of its symbols resembles pig pens or styes, kind of gives you the answer within that definition of the pig pen cipher. Which best describes a brute force attack? A brute force attack is an exhaustive search to attempt every possible mapping or key. The other options on here, intercepting and modifying data between 2 points, that's referring to a man-in-the-middle attack, and that's when your system's connecting to another device and a bad actor is intercepting that message and then modifying that data. The third option, when the attacker has access to both the ciphertext and the corresponding plaintext pairs, that is known as a known plaintext attack. And the last option here, that is known as frequency analysis. So in any language, there's going to be certain letters or symbols that occur more frequently. For example, in English, there's E, or the vowels A, E, I, O, U, followed by T and A and O, and so on. And this distribution of letter frequency is relatively consistent no matter the language, and it makes it easier for them to break an encryption. So this is a technique they use, frequency analysis. So again, the answer for question 21 for brute force attack is an exhaustive search to attempt every possible mapping or key. Question 22. What is a cryptographic attack in which an attacker has access to both the plaintext unencrypted version of a certain data and its corresponding ciphertext encrypted form? Well, we just looked at that. That is known as a known plaintext attack. So since we just looked at the bottom 3, we're just going to look at the Kasicki examination, which is a technique that they use to, one of the techniques that they use to break a Vigenère cipher. And the highlights on that is that it relies on observation when the same keyword is used multiple times to encrypt different parts of the plaintext. And for example, on the Vigenère cipher, if the key length has to be certain length to match the regular text, and so the key might be like the, and so they're able to find a pattern with the Kaseki examination. So again, the answer to question 22 is the known plaintext attack. Question 23, what is a prime number? I didn't put any options on here. The prime number is a number that is only divisible by itself, or the number 1. And the reason that they use prime numbers in cryptography is that it's just uniquely mathematical, and it makes for very good encryption. Question 24, what is 30 mod 11? So the way you're going to get the mod is going to be the difference of 30 divided by this 11. So you're going to have 11 and then 22, and then from 22 to 30, the answer is going to be 8 because that's the difference there. So if it was 40 mod 11, then it would be 11, 22, 33, and then you would have from 33 to 47 left over. Or if it was what is 15 mod 11, the difference would be 4. So you're basically just getting the remainder of that. So the answer again is 8. Question 25. Which of the following are symmetric stream ciphers? Well, the symmetric stream ciphers are RC4 and Cha-Cha. RC4 is a 40-bit minimum recommended. It's 1 round, and it's very weak encryption for wireless technology. Now, Cha-Cha, that was invented by Google, and what they call is Cha-Cha 20 because it has 20 rounds in there. It's typically about 3 times faster than AES software encrypted, and they do use it with TLS connections. Now, DEAR, that is a acronym that we use to help remember some of the asymmetric encryptions. So D on the DEAR stands for DSA, for digital signature algorithm. E stands for L-gamma. The next E stands for elliptical curve cryptography, and the R stands for RSA. Now, C32 braids, that is another acronym to help remember all the symmetric algorithms, and this is going to help you a lot. So C, that stands for cast. 3, that stands for triple des, so 3 DES. 2 stands for twofish. B stands for blowfish. The R stands for RC4, like -6, because there's RC4 and 6. A stands for AES. I stands for idea. D stands for DES, and then S means, hey, this is for this is all symmetric here. So that'll help you remember the different asymmetric and then the symmetric algorithms. So again, the answer is RC4 and Cha-Cha. What is meant by key size for question number 26? Well, the key size, it refers to the number of bits in a key used by a cryptographic algorithm. And then rounds is the number of iterations or cycles of processing that a cryptographic algorithm applies to the input data using a cryptographic key. So this is key length, and this is key rounds. And the larger the more number of rounds and the larger the key length, the stronger the encryption. However, a negative of using too much encryption is that it's going to take maybe too much processing power. It's going to slow down the network. And so companies try to find a nice balance between strong protection for the company as well as fast network speed. So again, the answer for number 26, it refers to the number of bits in a key used by a cryptographic algorithm. Question 27. What is meant by block size? So block size determines the size of the fixed length of blocks of data that the encryption algorithm processes at a time. The second option here, a ledger of transactions that offers several unique features, including transparency, security, immutability, decentralization, and can be public or private. That's talking about blockchain technology. A very famous one that you've probably heard of is Bitcoin, and that's a blockchain technology that uses that is public. Again, the answer to question number 27 is determines the size of the fixed length blocks of data that can be encrypted at the algorithm process at a time. Question 28. Which wireless security standard uses a 128-bit stream cipher for encrypted communications? The answer is WPA, which replaced WEP and took care of some of those vulnerabilities that they initially had there. Now, we did talk about WEP and VPN earlier, so now we're going to take a look at GSM, which stands for Global System for Mobile Communications, and it's now outdated, but that was used with 2G phones. However, now they use LTE to protect the 4G LTE. So the answer again to question number 28 is WPA. Now for question 29, employee Paris Wolf, that's me, sends an email to employee C. What does employee C use to decrypt the message from Paris Wolf? So my system is going to get the public key for employee C from the public key infrastructure, and it's going to encrypt that email with employee C's public key. And then when employee C receives that email, they're going to decrypt it with their private key. So the answer is employee C's private key. Now, if employee C was sending me an email, they would encrypt the email with my public key, and then I would decrypt it with my private key. Question 30. What is an example of asymmetric encryption? So if you remember earlier from the C32 braids, those were the symmetric encryptions, and then the DEAR. So RSA is an asymmetric encryption, and the MD, that stands for message digest, which is a hashing algorithm, because it goes in there, eats the message, and then spits it out. And then HA is also a hashing algorithm. And we know hashing is not encryption. So that really leaves us just here with the RSA. Question 31. Which four components involved in performing encryption are known to the party that will perform the encryption with counter cipher mode? So the party that's going to be performing the encryption will need to know the cryptographic algorithm, the cryptographic key, the plain text that they're going to be encrypting, and the nonce value. Since it's counter mode uses the nonce value. Now, if the question was rephrased to which two components involved in performing encryption are known to the party that will perform decryption before symmetric encryption is applied, so before, it would only be the cryptographic algorithm and the cryptographic key. If it was after, then it would depend on which cipher mode they would need. But they would certainly need to know the cryptographic algorithm, the cryptographic key, and the initialization vector if it was like a cipher feedback, for example. So again, with counter mode, this is the answer here. Question 32. Employee C wants to send employee D an email. Which key would be used to encrypt the message? So employee C is going to encrypt this email with employee D's public key, and then employee D is going to decrypt this message with their private key. Now, I do want to talk a little bit about asymmetric encryption. Asymmetric encryption always uses two keys, a public key and a private key, and every individual in the company that is using like an email exchange server, they're going to use a public and private key. With symmetric key, you may see that term as both a shared key or private and private key. So they would decrypt it with their private key, and then the other side would be private key as well. But that would mean that they're using the same algorithm and everything is exactly the same on those symmetric keys. Typically, you do see it as the term shared key, though. Question 33. What would happen to the hash of a file if it is rehashed after the first character of the file is changed? So one thing as an engineer, I want you to be able to go investigate and look things up. And that's what it takes to be a really, really good engineer, because a lot of the times you're just going to be looking up things. So let's take a look at that. If you don't know how to do something, then take a look here on Google and how to get the hash of a file on PowerShell. take a look here, get file hash. Okay, so this is the syntax here, get file hash. So now we're going to go over to PowerShell, and we're going to type in get. And as we're starting to type it in, I'm using the PowerShell ISE. It starts to fill it out for us. And you can click on there. And now the path. Well, if you're not exactly sure where the path is, you can go into the folder here, find the document that you want to hash. And in this case, we're going to use this Word document. And I'm going to left click it. And boom, boom, rename. No, just taking a look at all the options here. Oh, here it is, copy as path. So we're going to copy as path, minimize this here. I'm going to Control V it into this path here. And what is the rest of this syntax here? We're going to go back to the Microsoft here, and at the end, path, and then you see the string. We don't need that, we just need this algorithm here. Okay, so let's put that into, see, we start to type it out. And now it gives us all the different options here. So a lot of times you're going to be learning things like deprecated hashes, and then we're also going to be teaching the new ones. And the reason why that's really important is because all these IT systems, they give you all of the options of old to new. So when you're setting up a new system, the reason why it would have some of these older systems or options like MD5, or you're going to see like des, if you want to encrypt something, it is deprecated, is because what if you need backwards compatibility? So in some places, like let's say you're working in a hospital, they buy this really expensive $30 million machine, and they don't want to replace that. And so you're just going to use older IT algorithms or systems or operating systems, and that's why they still give you these options here. So in this case here, we're going to pick SHA-256, and we'll just tab that out, and we're going to get the hash of this file here. So the output's here, and now we want to open this file up. Okay, so we're just going to change the first character, and we're going to put a space on the first character of this file. We're going to save it, and then we're going to X out of it. And now if you just push the up arrow on the PowerShell, it's going to repeat the previous command, or it's going to go into the history. And now, as you can see, we just changed only the first character. We put a space, and the hash outputs a completely different output. So if you just change one character on a hash, it's going to completely show a different answer. Okay, so the answer is the entire hash is different. Question 34. What is the output length of SHA? So I'm just going to show you the diagram here of 160 bits, and here's what the hashes look like. So an MD5 is going to be 128 bits, or 32 hexadecimals, and the SHA is 160 bits. So bits are just ones and zeros, and the hexadecimal, this is what the hexadecimal looks like. So there's 40 characters here, and each of these individual, like the 5, this is made up of four numbers here. And so if you broke this down on the D, so here's 4 binary numbers, and then underneath the D, we'd take a look and see, okay, we're looking for a boom. And then this would be 1101. And so this would be 8 characters. And so that's why it's 32 times 4 is this 128 bits, because you're just seeing this 32 characters, but really it's 128 bits made up of these. And this one here is 160 bits. So again, the answer, what is the output length of SHA? That's 160 bits. And for MD5, that's 128 bits. Question 35. What is a LM password? Oh, hash password. So out of the two definitions here, used in Microsoft Windows to store passwords that are 14 characters or less, yes, that is a LM hash password. And then the other option here, each input of the passwords are converted to Unicode. So let me go ahead and show you what an LM hash looks like. And this is what a NTLM hash looks like. So as you can see, the LM had a lot of weaknesses because the length could only be 14 characters or less than 15 characters. And so they updated it to this newer hashing algorithm for the NTLM. However, the issue is that it sits right next to the LM. So if you take a look here, it has the same hash, and then it has the colons. And the NTLM has these colons in it, while other hashes like LM or SHA or MD, they don't have any hashes within the output there. And so the weakness here is that this is weak against dictionary lookups, and so is this LM hash. Let's see here. Do I have any other notes here? No. Answer: used in Microsoft Windows to store passwords that are 14 characters or less. What is bcrypt? So bcrypt specifically is a hash generator for passwords that uses salt to create non-reoccurring passwords, while like SHA or MD5, those are going to be general purpose hashing algorithms. So bcrypt is still a hashing algorithm, how it's specifically used with passwords. And so let's say you're logging into a website of Amazon.com. Well, when you type in your password of monkey10, it's going to add additional salt, which is additional characters to your password, and then run that through a hashing algorithm. And it's just more secure that way. 37. Is a rainbow table attack online or offline? So a rainbow table attack is offline. And how that works is whenever you are logging into, let's say, Amazon.com, and you put your username in and then you put your password in, they don't store your password because that would be dangerous if somebody got hold of your username and password within their database. And so what they do is they take that password and they add the salt to it, and then they store and then run it through a hash, and then that's how they store it in their database. The way when you do log in, they're able to verify you are and authenticate you. However, so this rainbow attack is referring to a bad actor has broken into their database, and now they have saved that database onto their own computer system, and they're using this rainbow table, which is a list of pre-computed hashes, and comparing that to the stolen data that they have, and see if they can identify if any of those rainbow tables are the same as that hashed database that they have access to. And if they can then try to go back and use your username and password to log in by kind of like a reversed lookup between the rainbow table and the database that they've broken into that's now stored onto their computer system. So again, the rainbow table attack is offline. 38. How does the ECB work? So this is a pretty complicated mode here, block cipher mode, or the ciphers in general. Whenever you see these cipher modes, the analogy I would like to use is it's kind of like a math algorithm where you have like multiplication, division, addition, subtraction, and it tells the encryption and how the data is going to, like the order of operations. And so this is the most simple cipher mode here. And block 1 here, that's referring to, this is just data, the first set of data. And it here with the key, this is a encryption method such as advanced encryption standard. And so it's taking the data, it's encrypting that, and then it's outputting this ciphertext. So what you really need to know about electronic codebook, this was the original cipher mode that they have, and that it's weak. Each block is processed separately. So if you had the same verbiage in block 1, like the house is green and the house is green in block 2 and block 1, this ciphertext is going to be exactly the same, which creates a weakness in the encryption and the cipher. And so there's no salting or initialization vector, And so that's why it says the same ciphertext will be output every time the same plaintext is encrypted, and that's very dangerous. And so now this is outdated. So question 39, how does cipher block chaining work? Well, let's take a look at the diagram here. So with cipher block chaining, we have the block 1 of data. That's just the first set of data. And then it gets put into, here's the initialization vector. So I want to take a look over here and imagine this is the block 1 of data. And then here, the initialization vector. So the first set of the initialization vector is completely randomized and generated. And so it takes the data and it compares that to the initialization vector. And depending on which operator you're using, like AND, if both the 1 and 1, then it outputs the 1. If it's a 1 and 0, then it outputs the 0. So then once this data comes down, goes through this initialization vector, this third line here, or the output, gets encrypted with whichever algorithm that you use, like AES, creating this cipher 1 text. Now this cipher 1 text now follows this line over here, and block 2 is now going to use this cipher 1 as the initialization vector. So it's exactly the same here, but now all the blocks are dependent on each other from the previous block, because this ciphertext is going to be the same exact size as the next set of data in block 2. And so I just want to take a little bit more time here with the AND OR and except OR, and take a look at these different options here. And because you may get something like this on your test here. So with a 1 and a 1, only one or the other have to be a 1 for the 1 bit to carry on, because these are just 1s and 0s in binary, and 1 means on and 0 means off when the machine's reading that. So 1 and a 0 carries down. It's a 1 and a 1. Okay, so OR pretty simple, and the except OR is 1 and a 1 comes down to a 0, 1 and a 0, 1, 1 and a 1, 0, 0 and a 0. So you do have to memorize these, because these are very, very probable that you're going to have something like this as a question. So question number 40. So I want you to match the definition. Okay, so ECB, or electronic codebook, that encrypts each block with the same key, where each block is independent of the others. And if we go back up to here, they're independent because they don't rely on each other like the cipher block chaining, where it's really depending on the previous cipher. So ECB would be encrypts each block with the same key, where each block is independent of the others. The cipher block chaining uses an initialization vector to encrypt the first block, and then uses the result of the encryption to encrypt the next block. Okay, yeah, we just went over that. And it's using the previous cipher to encrypt the next block here. So block 2, and then it gets XORed with the cipher 1, and then after the output, it's getting encrypted and turning into cipher 2, and so on until the message is complete. We'll just take a look at all the answers here. So for cipher feedback mode, uses a self-synchronizing stream on the blocks where the initialization vector is encrypted and XORed with the data stream. And on the future questions here, this should say question 40, but that's okay. On the future questions, I'm going to go over cipher feedback mode and counter mode. And counter mode converts from block into stream, and then uses a counter value and nonce to encrypt the data. 41, we're going to look at cipher feedback mode, output feedback mode, and counter mode. So for cipher feedback mode, the initialization vector is encrypted immediately, and it turns a block cipher into a self-synchronizing stream cipher. Now this key here represents something like encryption algorithms such as AES, DES, triple des, two-fish. And so the initialization vector gets encrypted, and then it's XORed with block 1. Block 1 is the data. If you are interested in how it works, I have the definition here of all the steps. However, for the purposes of this course, you just have to know that the initialization is encrypted. It's turned into a stream cipher, and it's taking the current block output of the XOR process. So what that means here is that what this outputting here, there's many different transformations and algorithms and math going into this output here, and a portion of this goes to cipher 1, and then the output of the XOR process here is used for the initialization vector for the next block. And so they're all dependent on the previous block, but it's not using the cipher 1 for the initialization vector. It's taking a certain mathematical formula. And that mathematical formula, for your purposes, you just have to know that it's taking the output of the XOR process. So output feedback mode, that is almost the exact same as the cipher feedback, as it's taking the block cipher and turning it into a synchronous stream output. But the difference is that it's taking the output from the cipher stage, and so it's just taking after this initialization gets encrypted with a algorithm, it's outputting different stages of the math, and so a portion of it goes to the block 1 data for cipher 1, and the other portion is using that for the initialization vector for the next block of data. For the cipher mode counter mode, you just need to know that turns the block cipher into a stream cipher. As you can see that all the data blocks, they're not dependent on each other, they're independent. And so that's why it's saying parallel processing, because any hardware that is processing this cipher mode can do it independently of each other, because each of these are not dependent on each other. It keeps track with a counter, and so each block of data goes up by one number, and this nonce is a one-time value. Question 42. What information protection method encryption has 128, 192, or 256-bit key size and a 128-bit block size? That is AES, and we're going to take a look at the other options on here. And one thing about the block sizes and the key sizes is that there's really no special technique to remember all of this information, and that you have to know all of these block sizes and these key sizes, and you have to have understanding of these transformation rounds and know the majority of this information here. So what is a transformation round? I felt like this is important because when you're reading the question, you should understand what it's asking here. So a transformation round is one iteration of the cryptographic algorithm or cipher processing steps. Each round involves a set of mathematical operations, substitutions, and permutations that transform the plain text into ciphertext. So what does that mean? Well, when we look at something here like AES and the transformation round, essentially it's a ton of math and computational for each single round. So when it has 10, 12, or 14 rounds, it just makes it that much more complicated to be able to decrypt. And during the round, it has all these different mathematical transformations or operations, substitutions, and permutations. How many transformation rounds does AES use with a 192-bit key? It uses 12 rounds. So 10 would be used for a 128-bit key, and a 256 would be 14 rounds. Take a look around here. As you can see, these are parallel with each other. 128, 10, 12 goes with 192, and 256 key size goes with 14. So you should definitely know that. What did NIST designate for the specification for hashing? So NIST is the National Institute of Standards and Technology, and it provides guidance and recommendations for encryption of electronic information and how to handle data. And so for hashing, they would recommend SHA. And for encryption, they have a few different ones, but one of the main ones they would say is the Advanced Encryption Standard, which is a very famous and most popularized encryption in the United States. And I just wanted to put a few different things here that they suggest here, such as the AES. This is the answer for hashing that they recommend is SHA. And there's different types of encryption, so they don't just recommend one type, but RSA, elliptical curve cryptography. For signatures, they recommend digital signature algorithm, and for key exchange, Diffie-Hellman or elliptic curve Diffie-Hellman. Question 46. What is a birthday attack? Okay, so a birthday attack is a type of brute force attack based on probability to create a hash collision, and we're going to take a look at that on the next slide. AES, that's an encryption formula. SHA, remember, anytime you see HA, I want you to think hashing algorithm. And a dictionary attack, that's when you go through and you try to use all different sorts of possibilities or combinations as if you're actually going through a real dictionary and you're going through a word list. A type of brute force. Oh, so I just want to repeat, a birthday attack is a type of brute force attack based on probability. So the probability scenario that they give is that if there's a set of n random people chosen in a room, they will have the same birthday. And so specifically, if they say if there's 70 people in a room together, there's a 99.99 mathematical chance that two of them will have the same birthday, which sounds crazy, but when you go through the math, it's true. And I want to talk a little bit about how the hash collision works and what is really happening with this birthday attack. So a hash collision is when we have two different inputs and they're producing the same output. So you can have one file over here that is not associated with this file over to the left, and somehow when they're put through the SHA-256 formula, or in this case the MD5 formula, the output is the exact same. And that can be dangerous because hashing is for integrity, verification, digital signatures, and password storage. And so here we have the two different file names here. One thing that they could use if the passwords were hashing out to the same, they could gain unauthorized access. If the digital signatures were hashing out to the same, they could pretend to be that other person. And for data integrity, as far as like a hash collision, why that would be an issue is if there's some sort of database, and that's how they verify that none of the data has changed. And so it could be tampered with or changed, and that change could go undetected. And that's why hash collisions are dangerous. And so the birthday attack is trying to find a way to take advantage of that and use that to the attacker's advantage. Question 47. A list of common words and tries. Each entry is known as a dictionary attack. So that's the answer there. A dictionary attack is a list of common words and tries. Each entry, dictionary attack. The option factors the prime number used within an RSA algorithm. That is talking about RSA factorization, or simply factoring the modulus, which in this course you do a little bit of the modulus, and that's why they teach you that, is because it's a technique of breaking the RSA algorithm, and it's also known as integer factorization, or it's used to recover the prime numbers. Matching the hash value back to the original text, that could be referring to like rainbow table cracking, where you have a list of hash files or passwords, and then you're comparing that to the database's hashed passwords, and you're trying to match that back to the original text. Looks for the rollover for the same value of initialization vector. That's a initialization vector reuse attack, or initialization vector rollover attack is what that's referring to. So again, a list of common words and tries. Each entry is known as a dictionary attack. So what is symmetric encryption? Symmetric encryption is when they use the same key that also decrypts the data. So they're using the same formula, the same variables or the same key to encrypt the data that they are to use to decrypt the data over here. The public key to encrypt and the private key to decrypt, that's referring to asymmetric encryption. Kerberos is a authentication server, meaning when you log into an enterprise environment, it's keeping track of your username and your password to be able to authenticate you are who you say you are. And that uses a ticket-based system. PGP, that stands for pretty good privacy, and is used for email encryption and authentication within the email. Question 48. Oh, the answer, same key that encrypts and also decrypts the data. Question 49. Data that is based on groupings of 128, 192 bits is a string or block cipher. So anytime it says in groupings of bits, like 128 or 192, you automatically know that it's talking about a block cipher, because blocks are groups or sets of bits, while string, that would be by one. And so the answer is a block cipher. Question 50. What is a symmetric string used for live stream transmission of data? So why is symmetric string used for live stream of data? So symmetric encryptions are faster than asymmetric. So that's one thing. And then the other thing is string is also faster than block encryption. And so the reason why they would use a symmetric string for live transmission, such as the news, is that it's going to be a lot faster and smoother. It signs files and encrypts that hash of the file to verify the integrity and authenticity. That's talking about a digital signature or the DSA algorithm for signing. The encrypts and decrypts in blocks of characters at a time with a complex algorithm. That is talking about a block cipher, such as ECB or the cipher feedback mode or the output feedback mode. Why is Diffie-Hellman used to distribute symmetric keys? Well, Diffie-Hellman is used to securely distribute the keys using asymmetric encryption to be able to go ahead and set up the symmetric encryption. Asymmetric encryptions are the key size are required to be a lot longer to be able to produce the same level of encryption as a symmetric encryption, and the asymmetric encryption takes a lot more compute power. And so with Diffie-Hellman key exchange, they want to go ahead and as quickly as possible switch from asymmetric to symmetric encryption. You can't just pass the keys over with symmetric encryption because it's not safe. So you need to distribute those keys with the asymmetric encryption, which is Diffie-Hellman. The other option here, it uses the same key to encrypt and decrypt large amounts of media. That's talking about a symmetric encryption. 1 bit at a time, that's talking about a stream cipher. So again, the answer, here we are. Question 52. Diffie-Hellman is vulnerable to what type of attacks? Well, because it's passing over the internet or over the network, it's going to be vulnerable to a man-in-the-middle attack. And the man-in-the-middle attack is when they're intercepting the data as it's being transferred, and they're changing and modifying that data. And usually they pretend to be one party or the other, or both. While the brute force attack, that is trying all different possible combinations of attacks. And a dictionary attack, that's a type of brute force attack where they go through a list of common words, such as a dictionary. A rainbow table, that's referring to a rainbow table attack, which is they're comparing a pre-computed list of hashes to a stolen database of hashed passwords. And again, the answer to what Diffie-Hellman is vulnerable to, that would be a man-in-the-middle attack. Which mechanism mitigates a copy and paste attack? So right off the bat, I want to go ahead and eliminate the message digest and the secure hashing algorithm, because those are hashing algorithms used for integrity purposes. And so we know it has to either be ECB or OFB. So we're going to take a look at the two different mechanisms and how that work and what exactly a copy and paste attack is. So with a copy and paste attack, they are receiving the data or the cipher, and slowly that they're trying to decipher that data. And with electronic codebook, if the same data is here as it is in block 2 and they're using the same encryption, they're going to be able to reveal what that encryption algorithm is by constantly resending and receiving those encrypted messages and decrypting it that way. Now, the thing with the output feedback is it introduces the initialization vector. So even if you had the same input over here as you had over here, the outputs are going to be completely different in these ciphers because of the initialization vector. So the output feedback mode mitigates the copy and paste attack because it's using this initialization vector and all the randomness that it's creating between each data. Question 54. Which one of these are associated with forward secrecy? Okay, so immediately we want to eliminate the options that are not possible. And so because we see MD, we know that stands for message digest, and then we see the HA here. So you want to think hashing algorithm. And so we know those are definitely not the answers here. Now this is elliptic curve Diffie-Hellman, which is Diffie-Hellman is for key exchange, and this is elliptic curve digital signature algorithm. So the answer is elliptic curve digital signature, or elliptic curve Diffie-Hellman, and I want to talk a little bit about the Diffie-Hellmans. So forward secrecy is referring to either perfect forward secrecy, and it means they're using ephemeral or a new key is generated with each new connection or session. So they're saying that the previous sessions will not be compromised if they were able to get the key of a current session. And so what that means is that if my device is connected to your device and we have a session, and during that session that we do have the like symmetric encryption set up, and originally we transferred those keys with the Diffie-Hellman, so asymmetric originally. If that session was compromised, if we had 30 days of past history, they're not going to be able to break it into the last 29 days. They only have the data from that one session. And so that's the benefit of having ephemeral keys, is that a new key is generated with each new connection or session. And these are the two different types of Diffie-Hellmans that use the ephemeral keys or perfect forward secrecy. Question 55. Which encryption component defines if a compromise of a long-term key prevents the compromise of any previous sessions? Well, we just looked at that, and that would be called the forward secrecy or the perfect forward secrecy. The other options here, the integrity check, that's referring to like checksums on a message or cryptographic hashes to see if the data has changed. This client hello and this server hello, that's talking about the TLS connections. And so when it's trying to set up the transport layer security, the device sends out a client hello, and then the server side sends out a server hello. I do want to go ahead and clarify that is different than the TCP connection, where it's sending the send, acknowledge, and this is specifically for security purposes of the TLS connection. And so the answer is forward secrecy. Question 56, what can XOR a pseudo-random number to create a unique cipher? And that would be the initialization vector. And so when we're looking at that, they're XORing the initialization vector, and we're going to take a look at the image here with the encryption algorithm and the data. And this is essentially, pretend this is the data, and then they're XORing it here with the initialization vector, the second line here, and this is a pseudo-random number, creating a unique cipher. We know it's not a hash, definitely know it's not a password, and we know it's not a symmetric key. And so the answer has to be the initialization vector. Question 57, how does chain block ciphering create randomness in the next block of data? So chain block ciphering uses the results of the initialization vector to encrypt the next block of data. That's the answer. The second option here increments the initialization vector to encrypt the next block. Well, it's saying increments, so you know that's the counter mode where it just keeps counting up. How does chain block ciphering create randomness in the next block of data? So with the first block of data, this is the data. It goes through this initialization vector, then it's encrypted, creating this Cipher1 text. And this Cipher1 text, the way it creates randomness in the next block of data is it takes this Cipher1 and then it uses this as the initialization vector for block 2. So block 2 is then XORed with Cipher1, and then it's put through this encryption to Cipher2. And then Cipher2 is then used for the next block of data for block 3 and XORed against that. And so specifically, like here's the block of data, and then here's the initialization vector, and then this is the result of the XOR, which then gets encrypted, creating this Cipher2. And that process goes on forever. Question 58, how is information about Bitcoin stored? First, I want to take a look at all the options on here. A command and control center, that is a centralized infrastructure or area or computer system that is controlling all the other devices in a malicious way. So a bad actor has their command and control center where they're controlling all their bots. The platform as a service and infrastructure as a service, those are for the cloud. The infrastructure, that's referring to you're renting hardware from the cloud service provider, and the platform as a service, you're renting the hardware in addition to all the infrastructure hardware devices are interconnected to each other, and you're able to just build directly your application or software in their cloud environment. So Bitcoin is stored in the distributed peer-to-peer network. I want to talk a little bit about what the distributed peer-to-peer network means, and that's a network architecture where multiple nodes or devices are connected to each other without a centralized server. I also want you guys to understand that all of these transactions are stored in a public ledger, specifically for Bitcoin, and that's a record of transactions or data that is publicly accessible and maintained by multiple parties in a decentralized manner, which is also known as blockchain. And so the public ledger allows anybody to be able to go and look up those transactions because it's public. So important information on blockchain, we're going to cover that here for question 59. So it's focused on protecting against someone spending money they don't have access to by storing it in a public ledger or blockchain. It's very computationally expensive to mine, and the rewards for mining are diminished over time. A transfer is considered when a transfer from one account ID goes to another account ID, and it's confirmed by the miners, which process all the transactions within a 10-minute period. When the transaction is recorded, it creates a new hash for the block and contains the previous hash, and it's building that transaction log. And the one main thing that's important to also very much know is that the owner of the Bitcoin has a private key, and they're using it to sign the transaction, proving ownership. And so if they're going to sell it, they're going to provide their private key to or whoever they're transferring it to that the other party, and then they're going to be able to verify it is the person that they say they are, and that's how these transactions are completed. Question 60. What is the length of the private key used to sign a transaction in Bitcoin? Well, the length is 256, and if you're interested, it specifically uses this elliptic curve digital signature algorithm. We're going to go through this Jeopardy game here. Let's go for encryption for $100.
Encryption for $100. What's the following true about this?
The bit key is a 40-bit key formed by selecting the 56-bit key, so C. Each round uses a different 48-bit key formed by selecting bits from a 56-bit key.
That's correct. That's correct. You have 8 bits for parity. Correct. Yep.
Standards and patents for $500. I'm feeling lucky.
What's the following were standardized by IETF? Remember, select all apply.
Oh, I need to phone a friend here. Standardized by the IETF. I'm going to go with the TLS and IPSEC.
Yep. These are good answers. Give me more.
And the X.509 certificate.
Give me one more.
And the Internet Key Exchange, is it all four?
All the above, correct.
Oh my
All the
goodness.
above.
Okay, this was a trick question. I don't like that. Okay.
Mm-hmm.
Standard and patents for $400.
Which the phonics simply became de facto standard by use.
The standard de facto, so something that everyone uses. That is going to be the Diffie-Hellman key exchange.
I
And
give you that one. Mm-hmm.
okay, I want to say the Galeas counter mode is a very common encryption. I know that now they use TLS instead of SSL, so I want to say like SHA is a good hashing as well for A, but I see a lot of SHA too, so I'm going to go with A, C, and D.
A and C and D. I will give you SHA. Remember, SHA-3 is the newest technology. It's only for early adapters. It's not very common. As you said, SHA-2 is the most common one. SHA-3 is only for the big adapters, so it's not very common. But remember, back in the days in the dot-coms, we have SSL v1, right? We
Mm-hmm.
jumped on the bandwagon. Everyone to do e-commerce back in the days. So we use SSL v1 for encryption and Diffie-Hellman for key exchange, right? Because that's the only two standards where back in the days, and everybody wants to do a .com something.
Okay, so this
So
was referring to
be
the history of the encryption. Okay,
exactly. So you have to
okay.
know how evolution technology. That is correct. Yep, we're looking how you understand how technology evolved.
Cipher modes for $100.
Where's the following true about CTR?
Okay, so counter mode. With counter mode, it is a block cipher to a stream cipher. So I want to say it does generate a unique nonce. So I want to say A, B,
Mm-hmm.
C, and ooh, I'm a little bit unsure about D. Can I
Mm-hmm.
phone a friend there?
The first question you ask yourself: CTR, is it stream cipher or is it block cipher?
It's a
So as
it's a stream cipher
mhm.
because it's block to stream. It converts it.
Right, exactly. So the end state it is stream, as you said. That's right. So A, I'll give you A. Now let's look at the unique nonce. In CTR mode, what we did is we replaced the IV with the nonce and counter combination, right?
Mm-hmm.
So if you notice the counter is 00, 01, 02. So the counter is incrementing per packet, right? Versus the
Yes.
nonce, it's F35 the first packet, F35 for the second packet, and F35 for the second packet. So really the nonce does not change by himself, but a nonce counter combination make this field changing per packet,
Ah, I see. That makes sense.
right? So
Yes.
now, so the nonce is not unique by itself because it repeats itself, but a nonce counter combination is going to make it better. It's going to make it changing per packet.
So,
And yep,
what's the exact answers on this one then?
A and D. Yeah.
A and D.
Remember,
Okay.
see, because as you said, CTR is a stream cipher, so we cannot use larger than a block size. So that doesn't make sense. Stream cipher is not a block.
Excellent.
Has nothing to do. It's a block of 1 bit.
Use Cipher
Mm-hmm.
modes for $400.
400. That's a good one. Now, which applying true about CBC or cipher block chaining? Again, first question you ask yourself is CBC a stream cipher or a block cipher?
Let's see here. So, cipher block chaining is a block cipher. So
That's
that would,
correct.
if you ever use the same initialization for two different messages, they will be encrypted with the same key stream. Oh, that kind of throws me off with key stream. I don't like that. So let me take a look at the
Mm-hmm.
next one. Cipher block chaining randomizes the plaintext by XORing it uh, with the previous cipher block. True. We know
Mm-hmm.
that's for sure true. B. Um,
Mm-hmm.
we know that CBC does not use a nonce. That's only counter mode, so C is not correct. The block cipher
Mm-hmm.
is used to create a pseudo-random stream of bytes, which is XORed with the plaintext. I would sub. I really like B.
B and only B. You are correct. Hence the concept of chaining, right? That's what the definition we previous block, right?
Yes, block ciphers for $400.
Which the following is generally considered true about AES.
So advanced encryption standard, I can tell you that it's best used for all symmetric uses. Well, all is a very large encompassing word, so let me take a look at the other options here first.
Mm-hmm.
While it's been broken, it's likely the best symmetric algorithm for most applications. I think that it depends on the variables that you use for the AES encryption. So in some
Mm-hmm.
cases, maybe it has been broken, but it's probably still the best. So I want to say B.
B and only B. That's correct. Yep. I mean, it's good use. I'm sure three-letter agencies have that capability.
Cybermath for $400.
Cyberman. These are one of the tough ones. Which the following pairs are considered coprimes?
Coprime. Uh-oh, I'm in
Mm-hmm.
trouble. What's a coprime?
Here's what we're going to say. So, in order to solve for coprimes, here's what you're going to do. You're going to write the factors of every number. So, for 9, what are the factors for 9? 1, 3, and 9. For the factors of 10, what are the factors of 10? 1, 2, 5, and 10. Now, how many factors they have in common between 9 and 10?
Not a single one.
The
Well, I
number
guess only
1,
one.
right?
Yeah, there's only
Right,
one.
one and only one. So if they share one and only one, the number 1, that's mean they are coprimes.
Oh, okay.
Right. How about 12 and 15? Let's see, 12
They
and
share
15.
other options, so those are
Right.
not
One.
coprimes.
Exactly. 1 and 3 right here. Because remember,
Wow.
in RSA, we collect two prime numbers, right? Two large prime numbers, but actually they are co-primes. They're not divisible by themselves. They don't share any factors. This is why you cannot guess one from the other in RSA. If I give you that number, you cannot guess it because they are co-prime. They don't share anything.
Concept for $100.
The easy one. What's the following true about salt?
I want to say they increase security. Adds a random values to the password,
Mm-hmm.
which then gets hashed. So that is increasing security.
Right.
It also creates randomness. And
Mm-hmm.
so A is the first choice.
Your
Concepts
selection.
for $200.
Place the following steps in the correct order. Challenge, handshake, authentication protocol.
Is that must be for passwords? So
Right. How you share passwords exactly. That was the old way to
mhm.
do.
So the authenticator sends a challenge to the peer, and the authenticator sends a new challenge to the. Don't they both challenge each other here? So that's going to be the server challenges, and the user also is challenging each other.
Here, one-sided. You just want to check the other end. Are they speaking the same language as you? Are they using the same hashing algorithm as you?
Really? Okay, so is it C
Mm-hmm.
then?
It should be the peer responds with the hash. So you send him a challenge,
Mm-hmm.
right? So he's going to hash it for you. Then you're going to compare the hashes between your calculation and their calculation, right?
Yeah.
And now, once if we are in agreement, that means we're speaking the same language, right? He's speaking French, I'm speaking French, because he responded to me with French, right? And then once we agree, that means the authenticator checks the response back to his own. So he's going to send a new one once we
Okay, so the
establish it.
answer is D. The peer responds
Right.
with a hash of known text.
So yeah, it's going to be if you organize these in the proper order, it's not only one. You're going to organize these in the proper order. So place these in the proper order. So it's going to be the order is going to be B, D, C, A.
Oh, BDCA, which
Right.
is okay. The authenticator sends a challenge to the peer. The
Right.
authenticator checks the response with its own hash of unknown text.
Mm-hmm.
The peer responds with a hash of unknown text, and the authenticator sends a new challenge to the peer. Oh, I was
Right.
misreading this question earlier.
Right.
That
Right.
okay. I definitely would
Same.
have got this, but it's I understand now what it's asking.
Right. It's just put it in the right order. Or
Okay,
right.
that's BCDA. Very good.
Correct.
All right, I'm ready for the next question.
Yeah.
Let's go with Cybermath for $100.
Ready?
Yeah.
Which the following is an asymmetric algorithm related to the following equation? Asymmetric and a.
This is the question for $100.
That's a tough one too.
Yeah, this is definitely a tough one. Related to the equation y squared equals x to the third power plus ax plus b. That's kind of looks like a one-sided algorithm to me. So versus like a symmetric side. So I'm gonna say RSA is asymmetric. Is that correct?
That's a good one. You picked an asymmetric, correct? Yep. Who's another one asymmetric? Remember,
Another
it's a non.
asymmetric would be elliptic curve.
Exactly. So that's elliptic curve. Remember, we generated the numbers in nonlinear fashion, right? Which is a y squared equal x cubed. So that's mean the numbers are not linearly related. So this is why it's harder to predict if you drive in a curve versus driving in a line, straight line. I can hard to predict whether you're gonna make a right turn or left turn, right?
Mm-hmm.
So
So the answer is D
so
then.
exactly, it's ECC, elliptical curve
Okay.
cryptography.
Learning a lot here.
So it's good, good.
Yes, definitely. I'm ready for a really tough one. Let's go with Cybermath for $500.
Okay, it's gonna be the easy one.
Okay.
This has a key space of what?
It has a key space of 56.
Right, so it's gonna
And
be
then has
2 to
8
the
bits
56.
for parity, right?
Right, for exactly. So 2 to the 56. That's our answer. Yeah.
And there was parity mean that can you tell me a little bit about parity?
Parity is for error correction and error detection. Remember, we reserved
Ah.
8 bits just in case if something wrong with the key, we can check whether the key had been changed or not changed, if it's correct or not correct.
So DES has a 64-bit key, but 56 are actually used for the
The usable,
algorithm, and
correct.
the last 8 are for the parity. Okay.
Right, exactly. Yeah.
Let's go with concepts
It's
for
it's
$500.
56 key. Remember, it's 56, right? It's going to be 56 key and 64 block, right?
Yeah.
Yeah. So which one? I'm sorry.
$500 for concepts.
That's a $500. That should be easy one.
Okay.
What hash functions are part of SHA-224, 256, 384, and 512?
I'm gonna say ABC. SHA-1, SHA-2, SHA-3. Wait. I take that back.
Uh-huh.
It's
Uh-huh.
B,
Uh-huh.
B and C.
Okay.
Oh wait, you only get to select one.
Exactly. So like one.
It's such a high SHA number, so it's got to be actually SHA-3 then.
Is it SHA-3? But SHA-3 we have what? 1024 and 0248.
Is it SHA-2?
Right. SHA-2. SHA-2 is the more, as you said, is the most common one
Okay.
nowadays, right?
I'm just guessing around
Right.
here. Okay. B.
Yep. B, and that's correct. SHA-2.
Okay.
Remember, SHA-1 is what? 160 bits. Only one size. SHA-2 has many flavors.
Okay.
And SHA-3 has many flavor and they have extra flavors.
So let's go with encryption for $500.
Hey, you're going all the way out.
Mm-hmm.
What's the fine trouble about PKI?
So public key infrastructure.
But
So,
here we're using what? DSA, digital signature algorithm. So right, so we're using PKI to establish DSA. How we do it?
well, if to digitally send a document, the sender uses their private key. So that is option D.
That's correct. That's your super secret autograph. You're going to autograph it with your super secret key.
And then the
Right?
recipient's going to decrypt your digital signature with the sender's public key.
Correct. So if I use your public key to decrypt it, I will guarantee 100% is coming from you and not your neighbor.
Okay.
Cool.
Let's go with encryption for $400.
Yep. Now again, the same thing, PKI, except in a different twist. Which the following is true about TLS SSL key exchange on a web server?
The answer to this is what's the answer to this one?
Now, when you log in to Bank America, right? So I sign in to Bank America. What's the first thing I do? I download the Bank America certificate, right?
Okay.
What information contained that information contained that certificate, which is the public key of who? Bank of America, right? So the person signing in uses the public key Bank America, but I generate a session key, I love Bank America, and I'm going encrypted using that public key. Who is that? Who's the only person in that world who can open that message?
Only the person that holds the private key that can decrypt it,
Which,
which would be
which
Bank of America.
America?
So you're going to
Correct.
sign in with the public key of the web server to encrypt the session key.
Right, and exact. So I generate a session key, and now they open it up. It's like, oh, yeah, in order to talk to Kusei, I am going to use I love Bank America session key,
Okay.
right? And we're
Yeah, that
going
makes a lot
to
of
switch
sense.
to symmetric encryption using I love Bank America. And you do it the same thing if you have three sessions, one for I love Amazon and one for I love Walmart, right? So you're going to open up different sessions, and everyone is going to use different key for every session for encryption and decryption. Make sense?
Yes, makes sense. So the answer is B.
That's correct. What do you think?
I want to do encryption for $300. We're on a roll here.
Yeah, we're going to close that category. Which the following is true about PKI? And again, this one is a trick one, just FYI, I'm telling you.
Okay. It provides for key management.
Give me more, a lot more.
It has
It's a
a
trick.
central authority.
Yep,
It can be distributed.
that's correct. You have delegate and proxy, you know,
Yeah.
root RAs, right? Exactly.
So A, B, and D?
And then GoDaddy and Intrust or VeriSign, they can talk to each other, right? To exchange information about status of different certificates.
Yes, they can. So it's A, B,
Right.
C, and D?
That's correct. All the above.
Okay.
That's why I told you it's a trick one.
Ah. Okay, I'm losing money here. Looks like I'm going to be owing you money.
No, no, yeah. No money will be awarded, just FYI, by this game.
All right, let's do encryption for $200.
First, the following are authentication protocols.
Okay. I'm going to say password authentication protocol, so B, and
Give you
then
that
D.
one. Hmm.
I never heard of those
That's
other. I
correct.
never heard of those other two.
Shiva, it is one. Shiva, it is the SPAP. The other one is yep, Shiva, it is correct. We use it. So B and C would be the correct answer.
B and
Shiva.
C. Okay.
Yeah, yeah.
I don't know anything about the Shiva. That's something I'm gonna have to research. Do you have any information on that for me?
Yeah, it's if you look right here, it's very easy. I mean, it's yeah, in the video notes right here. See Shiva. Yep, see, same. Extend PAB by encrypting username and password transmission. So it's
Wow. Okay.
enhancement to PAB. Yep. And here's your CHAB steps right here, and MS CHABs.
Awesome. Okay. Let's go with standards and patents for $100.
Which the following were standardized by NIST. Again, I'm looking at the historical data, looking at historical evolution technology, encryption.
I'm going to go with A,
Mm-hmm.
B, and D.
B, IPsec and Diffie-Hellman.
Yeah.
I give you A. HMAC, remember, was what? Hash-based message authentication code. So we use it what? For integrity, right?
Yes.
Now, if you use this one, integrity, I need something else for encryption.
For
What do I
encryption,
use
I
for
would
encryption?
use oh, is it that DES then?
That's exactly. Remember, back in the days in 1970s or something, we didn't have lots of technologies available. So NIST grabbed whatever was available to make it as a standard. So HMAC and DES were the only predominant forces at that time.
I see.
IPsec is IETF. Remember, IPsec was made what for the internet, right? So it was way mature technology, and Diffie-Hellman was for internet exchange key, right? So we can exchange the keys.
Okay. Makes sense. Let's go with Cybermath for $300.
Prime numbers.
That would be 7,
Mm-hmm.
23,
Mm-hmm.
and 7. ABC.
B and C.
Yeah, ABC.
A, B, C. Okay, good. And how about two? Yeah, two is divisible by itself in one, right?
Let me go with cipher modes for $500.
All the way. Okay. Where's the fine term about non-generated IV? That's a tough one.
D and
Mm-hmm.
A.
If
I'm
you
gonna go
use
with
it
A
as
and
a,
D.
if you use the non-size IV, we're just rebranding a non-size IV, so you're going to inherit the issues with the IV. Remember, one of the biggest issues we have with the IV is what? Back to the block cipher diagrams. Remember, in the previous designs, the IV was susceptible to frequency and pattern recognition attacks,
Mm-hmm.
right? After 500,000 packet, you should be able to decipher the IV, especially if you do Wi-Fi, right? Half a
Mm-hmm.
million packet, you should be able to break. This is why in CTR mode, we replace the IV with two parameters, the nonce and counter combination.
Mm-hmm.
And the counter keep incrementing, so you never be able to guess the counter, the number right here. So it's keep changing. So is the nonce can be used in IV not by itself. Remember, the nonce does not live by himself. He needs his roommate,
Okay.
which is the counter. So wouldn't be the better answer B?
Okay, so the answer is B.
Message number possibly combine other information, which is the counter. Hence, this is why we have a counter mode. So yep, B and D would be a better answer than A and D.
Excellent. B and D.
Mm-hmm. Cool.
Let's go for an easier cipher mode at $300.
Aside from more is a 300. Okay, you want to see that category? What's the find true about OAB?
So with output feedback mode, the plain text is XORed with the initialization vector.
Mm-hmm. Is it?
Yeah. And
Is it
oh,
directly XORed? Mm-hmm. Mm-hmm.
the plain text is XORed with the pseudo random string. Okay, actually, let me go with D. That's actually because it get plain text encrypted, XORed,
Exactly.
and then that's a pseudo
Exactly.
random string. Okay, so the answer is D.
That's correct. Yep. So if you look at the design,
Yeah.
if you look at the design right here, In the IV, we take the IV encrypted with the key, put in the mixer, then we do the XORing in the stream ciphers versus the block ciphers. The plain text is XORed directly with the IV.
Okay, I'm learning a
Plain
lot
text
here.
and put it then in mixer. And for PCBC, we take one more time the output and XOR to that, but then feed it to the next block. See how the design changed and the evolution technology and why we make it.
Let's go with cipher modes for $200.
We gonna clear that category.
Yep.
What's the find true about ORB? Give me two.
Let's take a look at the options here. I'm going to say that an advantage is decryption is exactly the same as encryption. I think that, Matt, it depends on which encryption algorithm that you use. But most likely you're going to use a symmetric.
Mm-hmm.
So I want to say A.
Mm-hmm.
And B, you don't need padding because it's a block cipher to a stream cipher. So with stream
Right.
ciphers, you don't need any padding.
Mm-hmm.
So we know D is not correct then, and I'm gonna say A and B.
That's correct. A and B, correct. Because yeah, symmetric encryption, the advantage. Remember, cryptography is symmetric operation. What do we mean? It's like talking and listening, right? You talk 50% of the time, you listen 50%. You can't just talk without listening. You can't just encrypt the data and never decrypt it, because you just ransomware yourself. And you're right, since this is a stream cipher, padding is not used at all. Make sense?
Yes, makes sense. All right, let's go with block ciphers for $200.
Yeah, ready? What's the fine true about AES?
Let's see here. So the algorithm is secret NSA level 1.
Mm-hmm.
It is the current standard for the United States, and it supports key sizes including 192 bits and 256 bits.
Is it NSA level one?
I thought so.
Is it secret?
Oh, is it secret? No, it's not. Oh, so everyone has access to this. So that's what you mean
Mm-hmm.
by so
Mm-hmm.
NSA level
Yep.
1 means only they have
Yeah,
access
secret
to.
NSA, right? Exactly. Nobody is not publicly published.
Oh, so that must mean that the answer has to be D then. So it's available for public
Exactly.
review, and the current standard is symmetric algorithm for the United States and supports key sizes including 192 and 256 bits.
Mm-hmm. Right. Right. Remember, if you log into your Wi-Fi router, you should be able to configure it. Right.
Yeah.
You better have AES on your Wi-Fi router. Yeah.
Let's go with block ciphers for $100. I need an easier one now.
What's the fine true about DES? Give me two.
It uses 16 rounds.
I
And
give you that one. Mm-hmm.
okay. Wow, the plain text is split into two 32-bit halves left and right. I didn't know that, but you have two possible answers on that. So
Mm.
I want to say,
Let's go to the basic math.
okay,
What's the key size for DES? What's the block size for DES?
the block size is 64. So I'm
Mm-hmm.
gonna have to
And the key
say
size?
A and
That's
C.
correct. The block, right? 64 is divisible by 32, and you're right. We split them into left and right halves. Right? 56 is not divisible. The key size is not divisible by 32. So B cannot be. So A and C would be the answers. That's correct.
Okay, let's go with block ciphers for $500.
All the way.
Yeah.
What's the fine trouble about two fish? This one, give me 3.
Let's say that two fish is much faster than AES. Two fish uses 128-bit blocks, and A.
Is much faster than AS or is it slower than AS?
Wait, since you have two options on here, it's computationally expensive to change the key into two fish. That would mean it's much slower. So that means the
Mm-hmm.
answer has to be A, B, and D.
That's correct. Remember, two fish. What is it? It has 128 block. It has 16 rounds versus AS has 14 rounds as a maximum. So 14 rounds is going to be always faster than 16 rounds,
Mm-hmm.
right? And it has 128, both of them. So they're tied for that one. But here's for computationally expensive because you can select, unlike AS has a preset sizes 128, 192, and 256. For two fish, you can select weird sizes, maybe 50, 150, and 250, you know. So that variability on the key size, it comes at a cost of more CPU power.
Okay, that makes
Okay.
sense. And
So
the answer here is
ABD, that's correct.
ABD. Let's go with block ciphers for $300.
What's the fine trouble about Serpent?
Let's see here. When compared to AES, Serpent is much less secure than AES, but much faster, which would be
Mm-hmm.
C.
It's a good answer.
Uh-oh. Oh,
Yeah, see, it's
multiple. I got to pick
well, it's
multiple to
one.
select all
No,
but
no,
one?
there's only one. Yeah, only
Okay.
one actually. But I just want to see how you read these convoluted questions and select the best of them.
Let's see here. Yeah, I would. AS has to be more secure, but maybe the other option for Serpent is that
Is,
it's going
is
to
it
be a lot
is
faster.
it AS more secure or is it Serpent more secure?
I don't know the answer. I would assume AES is the best if it's the most widely used
Right.
algorithm.
Remember, both of them were competitor to replace Des, but Serpent is going to use 32 rounds regardless of the key size. Whereas
Wow.
AES, you use that variable depends on the key size, right? So we use
Yeah.
10 or 12 or 14 rounds. Serpent doesn't care. It's going to be 32 regardless. But guess
Oh,
what? Yes. Back in the days in 1997 when they replaced DAS, or like predicting, when we have the competition, we didn't have as strong processors, right?
yeah.
Processors were not, so the need for speed was more important. So we selected speed over security. But
Wow, I didn't
nowadays,
even know that. Okay, so
our
Serpent is a
machines,
lot more
yeah,
secure. It's just that it's
right,
slower, so we're like, well, let's use this faster one. Okay.
right, because the processors were not strong back in the days in 1997. You know,
Yeah.
we need something faster than it's like, who's going to break it? Nobody has that processors anymore. But now you have a computer in your palm, right? So A would be a better answer. Serpent is much more
Yes.
secure than, but A is much slower.
I had no idea. Thank you for that.
Yeah, no problem. Yeah.
Let's go with concepts for $400.
Hash functions are said to be.
Well, hashes are not encryption, so they're one-way
Mm-hmm.
function, so B.
That's correct.
Hashes are resistant to collisions, but
Mm-hmm.
not foolproof, so B and D,
Mm-hmm.
and that's
You
all I
find the
have.
answer?
That's it.
That's correct. Yeah, resistant collision by adding salting, right?
Yeah.
Exactly. But not foolproof. Yeah.
Let's do concepts for $300.
Was that one Vigenère cipher? You find trouble about Vigenère cipher.
Let's see here with the Vigenère cipher. It's a multi-alphabet cipher.
Mm-hmm.
Oh, I thought there was a whole bunch of characters that are substituted for each plain text. Yeah, so each letter is mapped to a number and permutated with a simple math function and converted back. So is it B and C?
That's too complicated of an answer, right? It's too fancy.
Yeah. All right, give me
So
the
stick
answer.
with
I need
B.
help.
B is the only one. It's a polyalphabet, right? Remember,
Oh,
unlike it's Caesar in steroids, right? So unlike Caesar, Caesar shifts all the letters by certain number, right? Which is the default three, right? We shift all the letters by three positions. Versus Vigenère cipher is going what? Take the first letter can be shifted six spaces. The second letter can be two spaces. The third letter, so you're gonna have a secret word that going to tell you how many spaces every letter need to be shifted.
okay.
Right? So not all of them shifted in the same way. So at least if you can break, you're going to break one letter, but you can't break the whole letters. Make sense?
Yes, it does.
It's a polyalphabet.
And I thought
This
I
is
was
why
the
it's a poly.
cryptography master. Let's go with an easy one for cryptography math, $200.
Oh, that should be easy for you. You love
Okay,
it.
okay.
XOR the following.
Okay, okay. So we got, if it's a 0 and a 1, it always carries down to 1. If it's anything else,
Mm-hmm.
it's a 0. So we got 1, 1, 1, 1, 0,
Mm-hmm.
0, 1, 1, 0, 1. Let's see the answer.
That's correct. If they're different, it's one. If they're the same, it's zero.
Okay,
Right?
we need more of these. All right, let's
Yeah.
go with
Yeah.
standards and patents for $200.
Got it. Which the following were established by a paper written by 1976 by two master students at MIT?
They created Diffie-Hellman.
That's correct. We're looking for two master students, right?
Wow, they just combined their names.
Mm-hmm. Right. It is Diffie-Hellman, right?
Okay, let's go with standards and patents, $300.
Yep. The last one. Which the following have active patents? Active.
Active, huh?
Looking. What's the latest technology? Who's the newest kid in the block that everybody loves to use nowadays?
I don't know the answer to this one. Can I phone a friend?
Okay. How about that? AS and IPsec, they don't have patents, right?
Mm-hmm.
So what's left is between B and C.
I'm gonna go with B.
RSA have active patent, but remember like back in 19, when is it? It's already 20 years more than RSA. This is why now we can download an apps and authenticators for free, right? And you can
Well,
use it.
hold on. I want to go with ECC for my final answer then.
That's correct. TCC, elliptical curve cryptography, is the newest member. Why? If you notice, we are sprinkling elliptical curve DSA, elliptical curve Diffie-Hellman. See, we're sprinkling these guys now. Why? Because we go and generate numbers in nonlinear fashion because they're hard to break. Unlike RSA, it was a linear function when you generate the numbers.
Okay, great. Well,
Make
thank you
sense?
so much for joining me today, Kuse, for the Cryptography Jeopardy.
Yep. Good job finishing the board. Yep.
Any
And you take
final
exactly the
comments?
same. No, I mean, yeah, that's let's keep it up, and that should intrigue you and make you delve more into the material and try to understand it better. You
Absolutely.
know.
Thank you.
Thank you.